All right, then let's start. Well, usually the PhD defenses, they begin like weddings, like we are all gathered today for, except that today it's a bit special. So yes, indeed, we are all gathered for the defense of Susana Marin Aguilar, with this PhD entitled Local Structure and Dynamics in Dense Colloidal Systems, from patchy particles to hard spheres. So Susana, you will have about 45 minutes, if that suits you, after which we'll engage in the discussion with the jury. I will briefly present the members of the jury in alphabetical order. So we had Luca Cipelletti from Montpellier University, who was a referee, Daniele Koslovic from Trieste University, who was a referee as well, Marjolaine Dijkstra from Utrecht University, Kirsten Martens from Université Grenoble-Alpes, Giuseppe Fofi, Frank Smolenburg, and Rick Wenzink, who were the advisors of the PhD from Paris-Saclay University, and myself, Emmanuel Trizac, from Paris-Saclay as well. So please, Susana, the stage is yours. We are listening to you.
Thank you. Well, welcome everybody, and thank you for being here. So as Emmanuel said, today I'm going to present you some of the results that I got from my PhD. The title of this presentation and about this thesis is Local Structure and Dynamics in Dense Colloidal Systems, from patchy particles to hard spheres. And then my three supervisors were Giuseppe Fofi, Frank Smolenburg, and Rick Wenzink. So let me first give you a brief outline about what is going to be about this talk. So first, I'm going to start with an introduction. I'm going to talk about what is a glass. Then I'm going to talk about what are the characteristics of the glassy systems. And then I'm going to jump to the role of the structure in the glassy dynamics. After that, I'm going to discuss first how to control the dynamics by modifying the local structure. In there, I'm going to focus in patchy particles. And secondly, I'm going to discuss about how to predict dynamics from structural information. In there, I'm going to focus in hard sphere mixtures, and then I'm going to talk a little bit about machine learning. So let's first start with what is a glass exactly. So if we have a liquid and we decrease the temperature sufficiently rapidly, or we compress it sufficiently rapidly, we are going to end up in a new phase called a glass. But what are the characteristics of this glass? So if we see it in a molecular level, for example, we will see that this state is completely disordered. It doesn't have a long range order. And actually, for example, if we would like to compare a liquid, a dense liquid, and a glass, we wouldn't be actually being able to distinguish which one is the dense liquid and which one is the glass. The other thing is that because we decrease the temperature sufficiently rapidly, the particles are not really able to sample all the phase space. And then it is a system which is out of equilibrium. And moreover, it is an arrested system. So in general, we could say that a glass is a system that cannot relax in the experimental amount of time. So for experimental amount of time, I'm referring, for example, in simulations, the actual time that I'm going to do the simulation, or the actual time of the experiment. So of course, this is a really broad definition, and lots of different systems, they can have this type of glassy phase. In particular, for example, we can distinguish between metallic glasses, some molecular glasses, colloidal glasses, and there have been seen also some of these glassy dynamics in spin glasses. But in this talk and in general in this thesis, I'm going to base on particularly in colloidal glasses. But one thing that happens is that before the liquid completely falls out of equilibrium, before arriving to the glass, there start happening some characteristics in the dynamics that are different from the ones that I would expect from a liquid. And I'm going to list the two main ones of the dynamics. And the first one is related with the relaxation time. So the relaxation time is the time that the system needs to actually decorrelate from the initial configuration. And let's take, for example, a hard sphere system. So in here, I'm showing you the relaxation time of a hard sphere system. So in the y-axis, we have the relaxation time, and in the x-axis, we have the packing fraction. So at really low packing fractions, I'm expecting that the system is in a fluid phase or in a liquid regime. So the particles doesn't really need a lot of time to recorrelate from the initial configuration. They are just flowing there. So the relaxation time is really low. But what happens if I avoid crystallization and I start increasing the packing fraction? In there, I'm going to see that the relaxation time starts increasing sharply with little changes in the packing fraction. I can see that, for example, the viscosity starts increasing, the relaxation time starts increasing as well. And if I keep on increasing and increasing this packing fraction, the particles are going to start getting together and closer and closer. And an effect that appears in the Glassy dynamics is something called the cage effect. So let's, for example, take in a colloidal system, if I step in this dark blue particle, I will see that it is going to be caged by their neighbors. And these neighbors are going to be close enough that they are not going to allow this dark blue particle to diffuse. So in order to this particle is able to diffuse, it needs some collective rearrangements in the whole system that allow this cage to open and the particle to diffuse. So something that I would like to remark is in here, even if it is started to change from the liquid, we are still in equilibrium because the particles actually are able to equilibrate. If I keep on increasing and increasing the packing fraction, in some point I won't be able to actually relax. So in that moment, I'm going to be in the glass phase. But in this region where the relaxation time is changing, but it is different from the one that I would expect from the liquid, I'm going to call it the glassy regime or the supercool liquid. So one of the main characteristics of the glassy regime is that we find an extreme slowdown of the relaxation time with little changes of the packing fraction or in little changes of the temperature, depending on the system that we are looking for. Another thing that we can see in the glassy regime is something called dynamical heterogeneity. So let's take, for example, a glass former. In here, we can follow how it's going to be the dynamics of each particle. And at really short times, the dynamics are going to be homogeneous. All the particles start diffusing without any problems. And I can see it's quite homogeneous. But as we know, there's this cage effect happening in the glassy regime. And then in a time t equal, let's say t start, I'm going to see that the system is actually divided in regions which are going to have faster dynamics than others. So for example, here I'm going to see some regions that are slower and some regions that are faster. And of course, this I could relate it in some sense with the cage effect because some of the particles are going to be able to break the cage before some others that are going to need more collective rearrangements to actually decorrelate. So it seems that the glassy dynamics, it's easy and something that is quite well studied, but nowadays there's still some open questions that are remaining to be answered. So for example, one of these is what is the nature of these rearranging regions? How these regions, for example, scale by going deeper into the glassy regime. And also something that it has been studied in the recent decades is if these changes in the dynamics, these anomalous dynamics, is going to be related with some changes in the local structure. So these ideas in particular about the local structure, they started being in the mind of the people for a really long time now. And actually the first person probably that thought about this, it was Sir Charles Frank in the 1950s. Where he has this seminal paper where he asked himself how to arrange 12 particles around one. So the two answers that we can have immediately is that we can arrange it in an HCP unit cell or an FCC, which these two are related with the crystal. But he thought, well, there's an extra solution that we can arrange 12 particles around one. And this is the Dicosata cluster. So this Dicosata cluster is quite particular because it minimizes the local energy, for example, of the Lennard-Jones potential. And also because now I'm in the glassy regime, the particles are getting closer and closer. And it is really likely that for one particle, I will have 12 particles surrounding one. So actually he said that it was quite probable that we will find some Dicosata clusters in the glassy regime. And another characteristic of this Dicosata cluster, it is that it has a fivefold symmetry. This fivefold symmetry means that the Dicosata cluster cannot tile the entire space. So with this, in some sense, if we find these Dicosata clusters in the glassy regime, we're introducing some geometrical frustration to the system that it is not allowing the system to crystallize. So this could be related with the characteristic of a glassy system, which is avoiding crystallization. So of course, this in 1950s, it was mainly just ideas, and it was quite hard to actually see it in experiments and of course in simulations, but these ideas were inspiration for lots of different simulations, experiments, and also in theories. And actually, in the recent decades, there have been an introduction of a new theory called geometrical frustration, which is, says that in the glassy regime, we are going to see that the system will be formed for these local favor structures. So these local favor structures are going to have two main characteristics. The first one is that they are going to minimize the local free energy of the system. And the second one is that they cannot tile the space. So they are introducing some geometrical frustration. So from here, we can see that the Dicosata cluster is actually one of these local favor structures that we are going to find in the systems. With this, it was the inspiration of different experimental work and different simulation work. And here I'm going to show you just a couple of examples of things that have been done in different glass formers. And in particular, in the group of Paddy Royal, they have done some simulations about a one-strong mixture, which is a type of glass former, quite well studied. And they found that by going deeper into the glassy regime, by decreasing the temperature, the number of Dicosata clusters starts increasing with the slowdown of the dynamics. So in here, for the one-strong mixture, we find that the local favor structure is Dicosata cluster. But this is not all. There are other types of glass formers. And for example, in the same group of Paddy Royal, they saw that in experimental hard sphere mixtures, they found that also by going deeper into the glassy regime, in this case, by increasing the packing fraction, they found that the number of Dicosata cluster increased with the glassy regime, but not only the Dicosata cluster, also another type of defective local favor structure also started increasing, which is the defective Dicosata cluster. So these two clusters are quite related. Both of them are based on Dicosata cluster. The only difference of the defective Dicosata cluster, it is a lack of two particles in one of the phases. And well, we can see that these two are quite related. But there are other types of glass formers that have different local favor structures. And this is the case, for example, of the co-Vanderson. So in here, Daniele Kozlovich and co-workers, they show that in simulations of co-Vanderson mixture, which is a glass former of metallic glasses, they found that by going again deeper into the glassy regime, the local favor structure in here, the twisted bicap square prism, starts increasing by going deeper and deeper into the glassy regime. So one thing that I would like to remark in here is, as you can see, for different types of glass formers, the shape of the local favor structure is quite different. So in general, the interaction potential influences the shape of the local favor structures. So we have seen this is also accompanied by the slowdown of the dynamics. We have seen that for different glass formers, we have the local favor structures. And now we can start thinking a little bit further. And we can ask ourselves two different questions. The first one is, can we now control the dynamics of these glassy systems by modifying its local structure now that we have seen that it's really related, these two quantities? And secondly is, if we know that there are some changes in the structure, can we predict the dynamical behavior of glassy systems by only knowing structural information? And in this talk and in general in this thesis, I would try to answer these two questions. So for answering these two questions, in general, we take some inspiration on colloidal systems. So colloidal systems are an ideal playground for studying glassy systems. And this is because they have lots of different advantages. The first one is that the size of the particles is sufficiently large that we can actually follow them quite well in experiments, for example, with confocal microscope. So with this, we can actually see which are the structures that are changing and we can follow the dynamics. And moreover, it has been shown in this seminal paper of the 80s that in the hard sphere mixture, by going deeper but going by a higher packing fraction, they find that by introducing some polydispersity, we found a glass space. So actually the colloidal particles are going to be really useful for studying glassy systems. And they have been actually used, for example, for studying dynamical heterogeneity, to study what are the changes in the structure. And also they have been used for testing some theoretical predictions, for example. Moreover, another advantage of colloidal particles is that we can control and tune quite well the particles. In particular, we can play with the shape of them, particles. We can change and modify the size distribution of the particles. And finally, we can play a little bit with the interaction of the particles. And it has been seen that for crystallization, by changing the shape, by changing size distribution, and changing the interaction, we can enhance different types of orderings. For example, by using cubic particles, we can enhance a cubic crystal. So in general, by playing with these three characteristics, we can change the structure, the general structure, and then we can ask ourselves, we can use these three characteristics for changing now the local structure of a Glassy system. And the answer is going to be yes. And in particular, we are going to use this last one, the interaction, for answering the first question. Can we control the dynamics by enhancing some structures? So for this, we are going to introduce some directionality. We're going to play with the interaction of particles by using patchy particles. So what are these patchy particles? So we are going to use a type of model called the Arken-Frenkel model, which in general is about having hard spheres decorated with attractive square well patches on the surface. So with this, we are introducing a directionality, and we can control several parameters from the patchy particles. For example, we can control the size of the patches through this angle theta. Also, we can control the surface covered by the patches. And actually, this is one of the advantages that with the patchy particles, we can range between two extreme cases. By having a surface coverage of 0, we have a hard sphere, the hard sphere limit, and by having a surface coverage of 100, then we have the other extreme limit, which is a square well. As we are introducing the directionality, on two particles are going to interact attractively only when the particles are in the range of the potential, like in here, and when two patches are face to face. These are the conditions that the particles have to fulfill. An extra parameter that we can control from the patchy particles is the number of patches that we're going to have in the surface. And in here, I'm going to show you some results from systems with patchy particles with between 3 patches up to 20 different patches. And the way of locating these patches on the surface of the particle is by maximizing the distance between 2 patches. So this actually gives us some particular solutions for certain number of patches. For example, the n equal to 8 and equal to 6, they correspond to locate the patches on the vertex of some platonic solids. And in particular, n equal to 12, it will correspond to locating the patches on the vertex of an icosahedron. So this one in particular is going to be really important in the following slides. So it is nice to remember this particular geometry. So how are we going to study all of these things? We are going to use event-driven molecular dynamics. So this type of molecular dynamics is special for discontinuous potentials, such as the hard spheres and the square wells, which are the ones that we are going to use. And a thing that we would like to have is the avoid crystallization. See, this is one of the first things that we have to deal with. And one way of avoiding crystallization is through modeling binary mixtures of different sizes of particles. So in here, we're going to use systems with a 50-50 mixture of different sizes and a size ratio of 0.83. So this particular size ratio has been well used in square well systems, and it has been shown that it is able to avoid crystallization in a wide range of parameters. However, with the patchy particles, things can change. And actually, for a certain number of patches, we found that we still crystallize. But in here, I'm going to show only the results about the systems that are able to avoid crystallization in here. We're going to model our systems with a high packing fraction of 0.58, which ensures us that we are going to be in the Glassy regime. And finally, we're going to have a short range interaction potential of 3% of the particle. Moreover, we're going to explore different temperatures to see how the role of the patches start appearing with different temperatures. Now we need to focus in characterizing the system through the structure, the local structure. And for this, we're going to use 2 main tools. The first one is the topological cluster classification algorithm, and the second one is the bond order parameters. For the first one, it is based on identifying the neighbors of the particles through a modified Voronoi construction. From there, it builds some simple clusters of just a couple of particles. And with this simple cluster, it builds more complex clusters that actually they are clusters that minimize the local energy for certain potentials. And in particular, we are going to focus in the icosahedral cluster, which we have seen that it is really important in glassy systems. On the other hand, we have the bond order parameters. The bond order parameters, they don't give us information about particular cluster, and they characterize the local structure of the system through an expansion of spherical harmonics. So these ones are going to be also quite useful. In the side of the dynamics, we are going to characterize our system through calculating the relaxation time of the different systems. So we are going to define the relaxation time to 0.3 as the time where the intermediate scattering function has decayed to 0.3. So with this, we can characterize well the dynamics. So let's go to some results. So in here, one thing, an extra thing that I should mention is that we have different types of particles with different patches, and we need a fair comparison between them. So for example, if we fix the size of the patches, we are going to not to compare quite well the different systems. So we fix the surface covered by the patches, which actually corresponds to fixing the second virial coefficient. So with this, we are going to have a fair comparison between the different systems. In the side of the structure, we are going to calculate the icosahedrality, the number of particles involved in icosahedral clusters, and in the dynamics, the relaxation time. Let's go through some results. So at really high temperatures, I can expect that all my patchy particles are going to behave the same, as they are going to have sufficient kinetic energy. They're going to behave mainly like hard spheres. And then I'm expecting that the structure and also the dynamics of the different systems are going to be mainly the same. But if I start decreasing the temperature, then I can see some different effects with the patches and also in the dynamics. So first of all, I'm going to show you an intermediate temperature, the temperature equal to 0.6. And I can see, for example, in here, that for most of the patches, all the number of icosahedral clusters is mainly the same, excepting for 3 different number of patches, the 10, 11, and 12. So where I can see that there's an increase of icosahedral clusters in the system, which is also reflected in a different dynamics with the different patches. So in here, I can see that there's the slowdown with the different, with the 10, 11, and 12 patches. What happens if now I start decreasing the temperature? I will see that the number of icosahedral clusters starts increasing, the number of particles in icosahedral clusters, and this is reflected also in a slowdown of the dynamics. And I can keep on doing this, decreasing and decreasing the temperature, up to I found a temperature that I cannot relax anymore, where the system, it has entered into the glassy, in the glassy region, in the glass phase. But in the temperature of 0.38, where I can still equilibrate the system, I can see that, for example, for the 12 patches, almost more than 50% of the particles are involved in icosahedral cluster. And if I compare it with the other number of patches where there are mainly 0 icosahedral clusters, this is quite impressive. And also we can see that for the dynamics suffer an extreme slowdown of the dynamics by enhancing these icosahedral clusters. And actually, if for this 12 patch, I can see that there's a difference of at least 2 orders of magnitude compared to the other patches. So with this, we can see that by using these 3 geometries, the 10, 11, and 12, we can enhance some icosahedral cluster, which are the local favor structure in here. And this promotes some changes on dynamics. We can control the slowdown of the dynamics by enhancing this icosahedral cluster. An extra advantage of the patchy particles is that we can follow the translational dynamics, as what we can follow as well the rotational dynamics, because we can see how the system rotates. So now we would like to ask ourselves, can we do this thing with the rotational dynamics? Can we arrest the rotational dynamics? The icosahedral clusters are going to have some effect in rotations. So we did a similar approach as in here in the translational dynamics. And in here, we, once more, we obtain a relaxation time, a rotational relaxation time through fitting a function an exponential stretch exponential function to this rotational correlation, and we define the relaxation time as the time where the rotational correlation function has decayed to 0.3. So once more, we calculate this for all our different number of patches, and in here I'm going to show you only the smallest temperature that I have and the intermediate temperature that we have. So in here we can see immediately that we have a different behavior. As we had before, only these 3 patch geometries, they would have an extreme slowdown. And in here we can see a monotonically increase of the relaxation time with the number of patches. So in here we're having a different behavior with the rotational dynamics. And this we can relate it with the behavior of the particles for rotating. So in order to rotate, the particle needs to break the bonds that it is having to actually decorrelate from the initial orientation. So with this in mind, we calculate the number of bonds per particle, and we actually see exactly the same trend. So if we start increasing the number of patches, the particles are going to have more bonds, and of course, they are going to need more and more time to actually decorrelate from the initial orientation. But this is not all. For example, we can also relate it a little bit with Dicosata clusters. As we know, in the 12th patch, we're going to have, most of the particles are going to be in an icosahedral environment. And these icosahedral they're really well packed, and they're having the ideal orientations that are going to make that this particle will have really a lot of bonds, which is going to be reflected in a really increase of the relaxation time. So with this, we can see that for the rotational dynamics, we have the interplay between the number of bonds and also between the structure, in particular, the icosahedral clusters. So another thing that I would like to remark before is the scale of the rotational dynamics. So in here, we can see an increase of 1 order of magnitude, but if you remember from the translational dynamics, we had an increase of at least 2 orders of magnitude, and in general, everything was much more slower than in here. And as we can recall, in the translational dynamics, we need some collective rearrangements to make the system to actually decorrelate. And something that we find in the thesis is that, for example, for the rotational dynamics, we don't need these collective rearrangements. The behavior of the relaxation time is more a local effect that it is related just with the cage that it is made by the neighbors that are surrounding the particles. Okay, so let me just give you some remarks about what we learned about the patchy particles. So, well, we saw that in dynamics of supercooled liquids, we can control them by reinforcing some geometries that match with the local Faber structures. Well, and this we can use it, we can have it by using patchy particles that can be used to enhance some icosahedral clusters that are going to be related to some dynamical slowdown. And the rotational dynamics is also controlled with the structure and also with the number of bonds. So we have seen that the patchy particles are really good to change the local structure. What else could we learn from the patchy particles? And something that we started exploring is that, for example, in all of these simulations that I show, we use binary mixtures to avoid crystallization. But something interesting that we could have is a monoisper system. And actually, indeed, we explore some monoisperse glass formers. And here I'm not going to show a lot of results, but we show that the ability of patchy particles to modify the local structure can be directly used to the creation of monoisperse glass formers. So the modification that it is making to the local structure are enough to avoid the crystallization. And we are showing that by using patchy particles, we can increase the size of parameters that we can find a glassy system or a supercooled liquid. All of this is really interesting, and the patchy particles, we can use it really nicely. But then for having all these results, we need to introduce this directionality of the system. So we could think a little bit more in the future, and we can think if we can do exactly the same things, but now, for example, with some isotropic interactions or with a more simple particles. So for this, and also for explaining what happened with the dynamics related with the structure, we move to hard sphere systems. So in general, hard sphere systems, they have been well used for studying glassy systems. They have introduced that by introducing some polydispersity in the system, we have a region of different packing fractions where we can find the supercool liquid or the glassy system, and also we can find a glass phase. This by introducing a different size distribution. And we have seen, for example, that in 2D, this changes the general order of the system. Moreover, in the dynamics, it has been also shown that deep in the glassy regime, the dynamics of the system depends on the size ratio and the composition of the system. But exactly how this change is not really clear. And we would like to also see if this is related with some changes in the structure. So to answer these questions, we did a more schematical exploration of different size ratios and compositions of different hard sphere systems. So we use once more event-driven molecular dynamics of hard sphere systems. We use binary mixtures. We change the size ratio, and also we change the composition of the system. And moreover, we use polydispersed systems by changing the polydispersity of this system. We are interested once more in what happened in the relation between the dynamics and also with the structure. So now for the dynamics, we are going to explore it a little bit different. We are going to calculate the diffusion time, which is the time that a particle needs to diffuse 1 sigma. And we are going to explore all our different binary mixtures. So in here, I'm showing you the results for the dynamics. So let me walk with you in this complicated graph. So in the y-axis, we have the diffusion time. In the x-axis, we have the composition, and each of these lines correspond to a different size ratio. So the first thing that we can see here is that there's some non-monotonic behavior by the dynamics by changing the composition and by changing the size ratio. And for example, if we see that lower size ratios, they have, for example, a maximum at lower compositions. And if we go to higher number of size ratio, we can see that the maximum is actually shifted to larger compositions. So in general, it's not trivial the relation that there's with the diffusion time and with the changes on composition and size ratio. And another thing that I would like to remark is that in here, we fix the packing fraction to 0.575. But by fixing this packing fraction, we can see that the changes on dynamics is more than 1 order of magnitude by only changing the size ratio and changing the composition of the system. So now that we have seen this, we can ask ourselves, how is the structure? And also an important thing is that if we are going to find icosahedral clusters, and if these icosahedral clusters are going to be able to predict the dynamical behavior of the hard spheres, or they are going to be able to capture all the changes on dynamics. So we calculate icosahedrality, again, the number of particles involved in icosahedral clusters, which is the graph that I'm showing you in the right. And if we would like to answer the previous question, if icosahedrality is going to be used for predicting the dynamics, a quick answer is no. And why is that? Let's see, for example, the size ratio 0.6 and 0.65. We can see that the dynamics of these two are different. Not really different, but we can see an actual difference between these two. And if we see what happened with the icosahedral clusters, everything is mainly 0. So actually the icosahedral cluster is not really capturing all these changes on dynamics. Of course, I can see, for example, some regions that I'm going to have more icosahedral clusters that are going to be related with these regions of slow dynamics. So in some sense, the icosahedral clusters are capturing things, but not all the changes on dynamics. And if we remember from the introduction, the local Fabian structure of hard sphere is not only the icosahedral cluster, it is also the defective icosahedral cluster. So with this in mind, we started exploring different types of cluster, all the clusters that the topological cluster classification can give us. And we found that actually there's a big family of different clusters that have similar trends than the icosahedral cluster. So for example, in here, we have the defective icosahedral cluster. And all of them, they have these similar trends of the icosahedral, but none of them are capable of capturing all the changes on dynamics that we see by changing the size ratio and composition. And in these previous years, there have been an intense search of really simple local order parameters that are able to capture the changes on dynamics. And in particular, there have been some approaches to try to relate these changes on dynamics with the smallest cluster in 3 dimensions, the tetrahedron. And with these ideas in mind and everything, we found and we saw that all these types of clusters, we can decompose them in the smallest cluster of 3 dimensions, the tetrahedron. So we propose to characterize the local structure through the tetrahedrality of the local structure, which is just counting the number of tetrahedra that one particle is going to be involved in. So in here, we defined a tetrahedral cluster as 4 neighbor particles linked all together by distance. And this order parameter is going to quantify how well and how packed the clusters are. And for example, we can see the example of the icosahedral cluster. So in the icosahedral cluster, this is a cluster that is really well correlated with the tetrahedron. And actually, the central particle of this cluster is going to be involved in 20 different tetrahedron. This because each of the faces of the icosahedral cluster is going to form a tetrahedron with the central particle. So we can see here that at the end, it will be related with 20 different tetrahedron. So with this, we can calculate and we can characterize our entire system by just counting the number of tetrahedra each particle is involved in. And in here, I'm going to show you the results about this order parameter. And we find something quite incredible and quite nice. So in here in the right, I'm showing you the tetrahedrality of the local structure as a function of the composition. Once more, each of the lines correspond to different size ratios. And in here we can see that it is actually quite well correlated with dynamics. We can see that all the changes of size ratio, they are well captured there. The functionality of the 2 different types of regimes of size ratios is really well captured in this, with the tetrahedrality of the local structure. So in general, the tetrahedrality is capturing the changes of icosahedral cluster, but it is also capturing all the changes that we found with the other types of clusters that are related with the slowdown. Moreover, now we can compute the diffusion time as a function of the number of tetrahedra of all our systems. And we found something really nice. So in here, I'm showing you in the y-axis the diffusion time, and in the x-axis, we have the number of tetrahedra. And we see that for all our, for example, for binary mixtures, we have more than 60 different systems. They all collapse in one nice relation of the diffusion time and the number of tetrahedra. And this is not only for binary mixtures. In these full triangles in here, I'm showing you also the results of polydispersed systems. So in general, the tetrahedrality is capturing all the changes, the changes on structure for binary and polydispersed systems, and for a wide variety of different compositions and size ratios. So we have seen that for here, it works quite well. We can now see what happens if we go further away from the Glassy regime and also deeper into the Glassy regime. For this, we calculate the same quantities for different packing fractions. And we found that per packing fraction, each of them, the diffusion time follows a simple relation with the number of tetrahedra per packing fraction. So this is a really good result because now we can predict the dynamics of our hard spheres by only knowing the packing fraction where we are and also the number of tetrahedra each particle is involved in. And with this, we can capture the global dynamics of the system. So with this, we show that the tetrahedrality works really well for the global dynamics. And in the introduction, I mentioned that in the Glassy regime, we have the rise of dynamical heterogeneity. So we start seeing this different dynamic behavior in different regions of the system. So now we would like to see if the tetrahedrality is also capable of capturing these changes on dynamics in the local dynamics. So for this, we correlate the local structure and also the local dynamics. So in the local structure, we calculate the tetrahedrality per particle. And for the local dynamics, we calculate the propensity each particle has to move or to rearrange. We correlate these 2 quantities through a Spearman correlation. And in here, I'm going to show you one of our slowest systems, the correlation between these 2. And as we can see, we capture, the correlation is really well. It is more than 40%. We see that in general, this is an anti-correlation. So this means that regions of low tetrahedrality are going to be related with regions of fast dynamics. And we can color now each particle according to the tetradrality and to the propensity, and we can see if actually just by eye we can recognize the different regions of low tetradrality and dynamics. So I'm going to show you in here the result of the place where we have the best correlations. And in the left, I am coloring the particles according to the tetradrality, and in the right, according to the propensity. So just in here, we can actually see quite well that there are going to be some regions of low tetradrality that are going to be related with some regions of high propensity. And the same happens vice versa. We can actually see quite well these regions. So the tetradrality is capturing well the local dynamics, also the global dynamics, and this is for hard spheres. But now we can start thinking a little bit more in the future and see if we can apply this to other types of class formers. So we apply exactly the same tetradrality for now two different class formers, really well studied. The first one is a one-strom mixture, which is a system modeled by a Lerner-Jones potential, but the particularity is that it only retains the repulsive part. And with this, the local favor structures are really similar to the hard spheres. As we remember, they are Dicosata clusters. So we once more calculate the propensity of the system, we calculate the tetradrality per particle, and we correlate these two quantities. So in here, I'm showing you for the lowest temperature that we have a really nice correlation. Once more, it is up to 50% of correlation. We have once more the anti-correlation. So in general, it seems that it is working quite well also for the one-strom system. In the one-strom system, we have the advantage that we can control the temperature and we can go far away from the glassy regime by increasing the temperature. And as we increase the temperature, I expect that the dynamical behavior starts being more homogeneous as I'm approaching to the high temperature liquid. And actually, I can see if I correlate these two quantities that the correlation decreases by going further away from the glassy regime, which means that it is really capturing only the changes of the structure that are related with the glassy dynamics. Now we can apply exactly the same approach to the Cobb-Anderson mixture. So Cobb-Anderson mixture is a particular type of glass former used for metallic glasses. It is also used as Lerner-Jones potential, but in here it has a particularity that it is a non-additive system. So this will lead to have a different local favor structure. Once more, we apply exactly the same thing, and we see that in here, the correlations between the tetradrality and the propensity are really poor. They are less than 20%, and we miss this nice relation with the temperature. So it seems that the tetradrality is working well for the one-strom, but not really well for the Cobb-Anderson. So what do we learn from the tetradrality of the local structure is that we can actually predict quite well the dynamics of a wide variety of different hard spheres by only characterizing the number of tetraedra each particle is involved in. Also, the local structure, the local dynamics is really well captured by the tetradrality of the local structure. Some regions of high tetradrality are going to be related with some regions of low propensity. And finally, the tetradrality can be applied to different systems that have similar local favor structures, such as the one-strom mixture. The problem here is that we have different types of glass formers, and sometimes we don't know a priori which type of local favor structure we are going to deal with. So in general, we would like to have an approach that it is capable of capturing these changes on structure without knowing a priori which is the local favor structure that we're going to have. And actually, I'm going to show you some results about this and how to improve the prediction to other types of glass formers. So with the previous year, there had been really a big boom in machine learning. It has been applied now to lots of different fields. And in particular, it has been also applied now to the Glassy systems. So in general, the machine learning, we will have, for example, some data as an input. We're going to feed this input data to a computer. We're going to train this computer to learn from the input. And from there, we're going to get some output. For example, it could be a cluster, some type of data according to some information. We can feed some functions, and we can do lots of different things. But in particular, we are going to use this type of machine learning for clustering the types of particles according to the structure. And this has been already done for Glassy dynamics. And in particular, we can distinguish between two methods. The first one is supervised machine learning, and the second one unsupervised machine learning. The difference between these two is that, for example, in the unsupervised machine learning, we're going to use some of the expected output for training the computer to learn the features that we want. Let's see it in the Glassy dynamics. In the Glassy dynamics, our goal, in the Glassy systems, our goal is to capture the regions that are going to be prone to rearrange. So in the supervised machine learning, we are going to feed some dynamical information into the input, into the training, to learn which are going to be the particles that are going to be prone to rearrange or not to rearrange. So this work has been done by the group of Andrea Liu, and they have found that they can actually predict which are going to be the regions that are going to rearrange or not. The disadvantage here is that we need to know a priori the dynamics of the system. And in general, we would like to have an approach that doesn't know what is the dynamics of the system. So this is the case of the unsupervised machine learning. And actually, the group of Laura Filion, they have used this type of unsupervised machine learning in the recent years to actually predict and to classify particles that are embedded in different structural environments, for example, in crystal lattices, by only knowing structural information. So we are going to use exactly the same approach that they use, and we are going to apply it to the Glassy dynamics. So in general, we are going to have an autoencoder, which is something quite well known in machine learning. So it is a neural network where we are going to feed some input. In this case, we are going to use the structure. We need something to characterize the structure of the system. In this case, it's going to be the bond order parameters. And we trained this neural network such that in the output, we are going to recover the input, the bond order parameters, with a certain error. One particularity here about the autoencoder is that we have our input, we compress the information that we get in this bottleneck, so we reduce the dimensionality of our input by retaining only the most important information. And then with this, we decode this information and we obtain once more the input. An advantage in here is that we can, starting like we are just getting the important information in the bottleneck, we can get rid of the decoder once we have trained our system. And from here, it is easier to actually classify the particles. So from here, we can classify the particles that are going to be embedded in different structural environments. A priori, we don't know if this is going to actually work by, to classify the particles into the regions that are going to be prone to rearrange or to not. But we can try to this approach and see what is going to happen. So in this case, we are going to classify in two different families. These two different families, they can have some overlapping. So we are going to define per particle, we're going to assign a probability P of belonging to one family or to the other family. And now let's apply it to the Wannstrom and to the co-Anderson. So first of all, I'm going to show you here some of the snapshots of the Wannstrom mixture at the lowest temperature. In the left, we are showing the particles color by the propensity. And in the right, we are showing the particles color by the probability of belonging to, let's say, this red family. So it is really nice because we are seeing that in here, we can actually, just by eye, we can see that there are going to be some regions that have a higher probability of belonging to one family that are going to be related with these regions that have they are going to be rearranging in the future. So we can characterize the correlation between these two quantities, the propensity and the probability. And here, actually, I show you the results for the lowest temperature and the best correlation. And we can see that in general, the correlation between these two quantities is really nice and really high. So we have up to 60% of correlation. We have once more the nice relation with the temperature. So in general, the unsupervised machine learning, it is capturing a non-trivial structure. It is capturing the tetradrality structures that we found with the tetradrality, but also it is capturing some changes that we didn't capture with the tetradrality. Now let's go to our difficult system, the Cobb-Anderson mixture. And in here we found also something quite nice. We have an improvement of correlations up to 40% of the correlation. And in here, actually, if I show you also the snapshots, we can see that we can actually identify some of the regions that are going to be prone to rearrange with the higher probability of belonging to one family. And one of the advantages of the unsupervised machine learning is that we only need one snapshot to train our system, and it is really not costly in terms of computation. So in general, unsupervised machine learning captures these non-trivial structures related to the changes on dynamical features. And it is a really nice route that now we can use for predicting these changes on structure. So with this, I would like to finish. I am going to just give you some general remarks about the talk. So we learned that by enhancing some local favor structures, such as the Dicosata Clusters, we can control the dynamics of certain glass formers. We know now that we can predict the dynamics, the global and the local dynamics of a wide variety of hard spheres through calculating the number of tetraedra each particle is involved in. And finally, the unsupervised machine learning is providing us a new route to classify particles with similar structures that are going to be related with some changes in dynamics of glassy systems. And of course, with these results, now we have more questions and there are more things to apply in there. And in particular, in here, we are focusing in the tetraedrality. Now, we would like to see how this compares with some actual experiments of different hard spheres. So we have recently started a collaboration with a group in Florence, where they are doing the experiments and we are trying to see how the tetraedrality is well to predict the dynamics of the system. Also, now we are interested in seeing what happened with these regions of higher tetraedrality when we shear the system, what will happen above yielding and below yielding. And of course, in the unsupervised machine learning, then in there we have a wide variety of things that we can do. We can apply it to different glass formers and see how it works. And in particular, now I'm interested in applying it into the glassy systems. So I would like to see if this unsupervised machine learning is also capable of capturing these changes in structure into the glasses. And after this, we could apply it and to compare it with some experimental work that it has been already published. So with this, I would like to thank my three supervisors, Rick, Giuseppe, and Frank, because they have guided me quite well in these 3 years of PhD, and I'm really happy of being in this group. Also, I would like to thank Laura Filion and Emanuele Boattini from Utrecht University, with whom we did the collaboration for the unsupervised machine learning, and I learned quite a lot about, in general, about the unsupervised machine learning and machine learning. And Francesco Shortino from the Rome University, with whom we are doing a collaboration about the monoisperse glass formers, and it has been really interesting to discuss with him. And of course, the group in here of soft matter, in particular to Shaheli Mitra, she did the simulations about the Wanstrom and the Cove-Anderson mixture. And of course, the CONACYT, who has gave me the money to finish my PhD, and all of you that have heard me. So thank you very much.
Thank you very much, Susana, for this clear, well-delivered and articulate talk. I have to say that I am still flabbergasted by this tetrahedrality of the parameter. Yeah. Now we'll go to the referees for a round of questions. So the most distant one, I guess, is Daniele Koslovic. So please, Daniele.
Emmanuel, I'm the most distant one?
I think yes, in terms of...
Yes. Okay, well, Susana, thank you very much for your presentation, which I really enjoyed. And I also, well, I would like to say that I've been tracking your work since a little while, especially since I saw the paper about the tetrahedrality. I was really impressed by it. It's very nice. And also I would like to say that recently I tried to reproduce the analysis that Susana has done, and I can confirm the results are correct. So the work is not only very nice, but it's also scientifically sound and correct, which is very important, I think. So I also enjoyed very much reading your thesis, so the manuscript, which is very clear, well organized. It gives really a nice overview of the theory as well, and a great summary of your results. So it's a good work, really a good work. And so yes, so maybe I can ask a few questions. I'm while you were talking, I collected many of them to be a bit concise. So maybe I will ask you a few things about each of the chapters. So there is one part on more the patchy colloids, patchy particles. Then there is one on tetrahedrality, and then finally the machine learning. Okay. So so you didn't talk too much about the monodisperse patchy particles, but I was quite intrigued by your results. In particular, the idea that you can have a monodisperse glass former. So can you comment a bit more on that? So in the slide you show a phase diagram, which didn't appear in the thesis.
Yeah.
So what is the message there? So does it mean that your patchy particles with 8 patches are like a gel, and this is why you can cool them down without crystallizing? This is what comes out. So can you elaborate a bit more on that?
Sure. So maybe just I have it here, some slide just to give some general information about the monodisperse.
Yeah, thanks.
Then, well, so in here we are using 2 different patchy particles, n equal to 8 patches and the 12 patches, and we're seeing that the ability of these 2 particles to change the local structure are capable of avoiding crystallization. So with this, we explored different temperatures for these two systems, and we found that actually the 2 of them, they are capable of avoiding crystallization at low temperatures. So this was really nice. This is a low packing fraction, but it is really nice. But then in there, we found that, well, for the 12 patches, as we saw, it is going to enhance some icosahedral clusters. And then in general, the structure is going to be a little bit, I'm going to have, for example, this second peak, this split of the second peak, which is related with this icosahedral cluster and tetrahedrality in general. But the interesting thing that we found is that for the 8 patches, we found that the structure is mainly the same structure as a high temperature liquid. So even if it is not really enhancing this icosahedral cluster and not enhancing this tetrahedrality, we're finding that it is avoiding crystallization. So that's just for putting some context.
Yes. Yeah. Sorry, but then, now you show the dynamics on the right, and there you see that the slowing down is not that much. So I mean, this was one of the questions I had from reading the thesis. So is the system really glassy?
So actually, yeah, that's quite an important question, and it seems it is glassy because it has this, I don't have a picture, but it has the 2-step relaxation, for example. The only problem is that, for example, the plateau is really, really high. It is really an attractive glass, so the plateau is super high. And then if I could go deeper into temperatures by decreasing the temperature, the only problem here is that now the simulations, they take quite a long time. But I would expect that I could relax my system and have a slower dynamics and compare it also with the 12 patches. So, but then, yeah, if it is, for example, if it is more like a gel, I haven't really seen if it is percolating or something like that. I haven't really measured it. It might be. It is. I guess it is an arrested system. But then, if it is starting to reach to the gel phase, that I'm not completely sure. It might be. It would be. Yeah, you should.
In the phase diagram you show of your, in the collaboration with Francesco Fiortino, there was a gap, right, in the phase diagram, and the old argument they had with patchy particles is that by reducing the valence, reducing the number of patches, you open up this area, you can cool down the liquid, and it forms a gel.
Yes.
So this is what happens in your system, right?
So yeah. So the thing is, in here we're not reducing the balance that much, because if I remember well from those
right, they started from 5. I just looked it up. They started from 5 downwards, but maybe it happens already.
Yeah, but something interesting actually, and that's something that actually I didn't show in the thesis or anything, is that I also computed how was the distribution of bonds of the particles. So for example, in there, I wanted to see if it was more or less like all they were really well bonded or what was happening in there. And I remember that for the 8 patches at really low temperatures, most of the particles were actually bonded. So I don't know if it was like 40% of the particles, they had the 8 patch. So they were like doing a quite well structured, well, they were quite well connected. But then, I'm not so sure if it is actually a gel. Might be. Yeah.
So with the 12 patches, I have an intuition, of course, of what will be the local structure, right? But what happens with the 8 patches? How should I envision the locally favored structure? Did you do the TCC analysis on that system? What does it give?
Yeah.
I mean, I don't think it was in the thesis.
No, those things I didn't show. So actually I compared, for example, the 12 patches and the 8 patches. And of course, in the 12 patches, I have a higher number of Dicosata clusters and defective Dicosata clusters and the whole family of these local structures. But something quite interesting is in the 8 patches, it doesn't seem that none of these local favor structures are increasing with the lower temperatures. They remain more or less the same. So it is actually quite an interesting system, because it is, I don't have a clear answer of which one is the local favor structure of there. So I saw, for example, that they have defective Dicosata clusters as well. There's they were like, I don't know, at least 4. They have, and actually that I think I show in the thesis, they have quite a lot of defective Dicosata cluster. The Dicosata cluster, I don't find it that as a whole. But then there's none structure that is really increasing with the temperature. So it is something that it might be that the TCC is not capturing, could be. And but then
I mean, my point is that, I mean, they may not have a well-defined locally favored structure. It could be that this guy remains very much disordered, like liquid. So we had an argument like that in a previous paper with Dave Reichman, Glenn Ockey, you know that paper. So at least there was one model which was indeed monodispersed that didn't have a well-defined locally favored structure, and that was actually good to us. So it was the Gaussian core model.
Yeah.
So it seems to me that the physics you are describing resembles a bit the one of the Gaussian core model. But if this is the case, does it mean that your model is also mean field in some sense? You see where I'm heading? I mean, this is one thing that you may look at in the follow-up of this work.
And actually I don't have exactly super clear now the ideas, but I remember, so I also checked what happened with the Stokes-Einstein relation and how it breaks and the Stokes-Einstein divide and everything, and I found that in here it is actually not really breaking. So it was something I read in one paper, which I don't remember exactly what it was, that the systems are not really breaking from these relations. I can relate them in some sense to the mean field approximations, and they are going to have good predictions in there. So in some follow-up, I think it would be interesting to see what happened exactly.
Yeah, if you could go at lower temperature, then, I mean, another thing that would be interesting to do is to compare with the prediction of MCT, right?
Sure.
You can get the structure factors and just plug them in. It's very easy to do, okay? So, sorry, Emmanuel, one question. How much time do I have for questions?
Still have some more time if you wish.
Okay, thank you. So I'll make maybe one more question on these patchy particles very quickly. So, you show that rotations are always, let's say, decorrelated. They are non-cooperative, right? So they are decorrelated from the translational relaxation and so on. Can you think of a way to make rotations cooperative in some sense with your models? Is there a way to introduce some cooperativity in the rotations? Did you think about that?
Yeah, that I'm not so sure.
I mean,
I'm not really sure. Yeah, because the thing is that it was really local. I'm not so sure how to do it more like a more collective, because for example, we did this Monte Carlo, where we have just the gauge and then we rotate the particle to see what happened, and it was really a local effect. So how to do it exactly more collective, I haven't thought about that. It's interesting.
Okay, then I have a question about more the so the part on tetrahedrality. So I mean, this idea about polytetrahedral order, so not exactly icosahedral order, but somehow distorted icosahedral order, has been around for quite a while, right?
Yes.
So I mentioned a few papers where, I mean, this kind of approach has been taken, and in particular, I mean, another idea that you may have is that you look at tetrahedra and then you quantify how much they deviate from perfect tetrahedrality, right? And this approach recently has been applied with quite some success by Tanaka and his postdoc. So, I mean, I'm interested in that, but I would like to know if you have some insight how your order parameter connects with these other measures.
So actually, we didn't calculate directly the same order parameter of Tanaka, but I guess they are really well correlated because at the end, so the structure, for example, the Dicosata cluster, I would imagine that the tetrahedra are going to be well a nice structure and everything. So I'm seeing that they have a good number of tetrahedrality, but when they start getting distorted, I could imagine that this is more the case of the other clusters, like they have the similar trends, but they are not capturing everything, because I can imagine that they have some distortions in the tetrahedron and everything, but even in here, I'm capturing all those changes, not really having information about the morphology of them. So for example, I couldn't really say, okay, this region, it has a more distorted tetrahedron, and then that's the reason it is more related, I don't know, with changes on dynamics or something like that.
Just one comment. I mean, what I notice is that the parameter by Tanaka gives a strong correlation with the dynamics in terms of the propensity of motion, even at short times, while your doesn't. So by taking into account the distortions from tetrahedrality, you probably captures, you capture the defects, okay? So the particles that move a lot. Whereas your approach tends to cut on that, and you probably just get, you somehow lose a part of the
information.
Exactly. Yeah. So that may be one difference, okay, which may be relevant. So then I have one comment and maybe a quick question on the part on more connection with the dynamics, also with the machine learning part. So I have one comment. I mean, I think it's a bit of a misconception. You started off by saying that when you use machine learning, you apply a method where you don't want to know a priori what is the locally favored structure. You said exactly that. So but this you don't know even if you apply TCC or Voronoi. I mean, you just have a method, and then you look what's the result, right? And you identify the locally favored structure from the result of the analysis, right? It's not that you start a priori by knowing what. So
of course.
You shouldn't think that machine learning does, I mean, something different in that respect. You plug in some order parameters, some descriptor, and then you get some output. But I noticed the sentence, and since I know that many people say that, I think it's not correct.
I was thinking more like, for example, in the tetrahedrality, that now a priori I know that, for example, in glass formers that are going to have local favor structures similar to the Dicosata cluster, or local favor structures that can be decomposed by tetrahedrality, then I know that it's going to work well. That was like I know more or less a priori that it is, if I know that the local favor structure, then I know that tetrahedrality will work well.
Okay. Then still a quick comment on a quick question actually on the correlation between dynamics and structure, actually propensity and structure. On which time scale you get the maximum of a correlation? So I understand that the tau over there is not tau alpha, right?
No, this tau is the unit time.
Even in this is a quick comment. Even in the thesis, I had a hard time actually to make the connection with the time scale. So at what time does the maximum occur over there? So is it tau alpha? Is it longer than tau alpha?
So actually, I don't have it plotted in here, but for example, in here, I'm showing results of the average probability. So this is a little bit larger than the tau alpha, because we are taking into account a larger region, so we could expect that it's more related with larger alpha relaxation. But then if I take the correlations only about the probability, it is really the tau alpha, that I have the peak in the tau alpha. think so. Yeah.
Okay.
Yeah.
Okay, thank you very much, Susana. I would have many more questions, really, but I leave room to the others. Okay. So thank you very much.
Well, you can ask any questions by mail if you want, and
Yes,
I'm
sure.
going to be happy of answering them.
So thank you, Daniele. Well, of course, when I meant distant, it was in terms of geography, right?
Yeah, sorry, I didn't get it in the beginning.
Yeah. So then the next less distant referee is Luca. So please, Luca, it's up to you.
Thanks, Emmanuel. So I guess I am the more distant one in terms of research, being an experimentalist, but a bit less distant than Daniele. I would like to thank you, Susana, and all your numerous and very good advisors for inviting me to be a referee of your thesis, which I actually enjoyed a lot. I think that you did really cool things. And I would like also to congratulate you for your presentation, which was extremely clear and very nice. I mean, you were really able to distill the most important things of your work and present them in a very clear way. And I would like, on a lighter note, to congratulate you for being able to pronounce this awful word, which is tetrahedrality, without getting your tongue messed up for so many times. You never fail to say tetrahedrality. I think that I won't be able to do that. Whatever. Okay, so I have a few questions. One question is on the patchy particle system.
Yes.
And if I remember well, when people have done the mode coupling theory of the square well system, so with full coverage, no patches, they found this reentrant behavior in the temperature volume fraction phase diagram. And then there was a singular point at the tip of this reentrant region where the dynamics exhibit funny features. For example, correlators would have a logarithmic decay and things like that. And people have actually even seen things along these lines in experiments. People in the group of Wilson-Poon have measured correlation functions for this square well system, finding logarithmic decay. So I was wondering whether this kind of behavior is preserved in the patchy system or not, or maybe you just didn't look for it. It was just a curiosity.
Yeah, so I actually didn't look carefully to it. I just, for example, we captured the reentrance with the patchy particles, so that we recovered. We see the dependence with different coverage and everything, but I didn't follow, and I didn't really capture if it was more like a logarithmic decay in a certain points or if it was just the normal exponential stretch exponential. So that might be a really good thing to check and see if it is conserved also in patchy particles. So
okay, it was just a curiosity.
Yeah.
Then I had just a question which was inspired by figure 311.
Yeah.
Which should be, I think, page 45 or something like that of your manuscript.
Yes.
Where you discuss the amount of clusters that you have in your system depending on various control parameters. And you relate that to crystallinity.
Yeah.
And I was wondering whether when you do this kind of analysis, do you just look at the number of clusters, or do you also look at their spatial distribution? Because I guess that things may be very different if you have isolated clusters of more ordered regions, or you have a big mesoscopic region of your sample that is more ordered and all your clusters accumulate in this region, because that would be more reminiscent of a phase separation process or something like that.
So so in there, for example, I have the regions of I have the crystallization. So for those ones, well, in general, the TCC will give me the number of particles involved in each type of cluster. So for example, for the crystals ones, I don't know, like the example of the 14 patches, which is a system that will crystallize. I have, I don't know, 90% of particles are involved in BCC and an FCC way. So in those ones, I didn't really do lots of things. I just saw, okay, it's crystallizing. Okay, I don't analyze it quite well. But for the ones of the 12 patches, which have the Dicosata clusters, that I also check how were distributed in the space, because I was also quite curious if they were like kind of percolating, or they were having like a big cluster in there of only Dicosata cluster and the other ones were not really ordered. But at least the thing that I saw, it was they were like really well distributed in the whole system. They weren't really percolating or doing something. For example, we check about the lab spaces if they were trying to crystallize in a crystal that has an icosahedral in there, and we didn't really find that they were like doing some nice percolation or something. So it was really well distributed in space. So,
Okay, well, that's nice, I guess. Then I had another questions about the free spinners. So this would be, I think, page 56. Figure 4.3. Yeah, it depends on the version of the thesis, but it's figure 4.3.
With all the correlators?
Right, where you have this bump in your correlation function.
So
and
that I can show you here as well. I think I have one.
Okay, cool. And I like very much the discussion about finding the reason of that bump and the contribution of the free spinners, and I thought that was quite neat. But then I was a bit puzzled by one thing, which was that among these systems, I think that somewhere you have, it's not, okay, in the thesis, I think you have things plotted as a function of theta, which in some sense is as a function of coverage.
Yes.
And for the largest theta, you have essentially full coverage.
Yes.
So I would have thought that for the full coverage, you would also have free spinners, because if you have a full, if you have a patchy object, then I can understand that a rotation is hindered. But if you have an object which is a sphere with full coverage, to me that sphere should be able to spin as freely as a free spinner.
Yeah, of course. Yeah, but
you don't see that, right?
No, and in here, I think, for example, in that figure, I show, I think there's not the square, so the square well is not shown in there. So for example, for the first one, it is the 6 patches, and I have a theta, the highest one is equal to 50. So even if it is almost full covered, there are some regions and some spaces that are not covered by the patches. So at the end, this is hindering a little bit the rotations, because once the particle wants to rotate, it actually needs to jump from one to the other side to break the bond and to rebond after it rotates. So I think that's the reason I'm not seeing actually the free spinner there. But if I see, for example, a little bit more careful, they start having this decay a little bit more, I don't know, it changes a little bit the decay at the end of the correlation, which in some sense, I think it might be a reminiscent of the free spinner, that it is about to cross to the actual free spinner completely if it is fully covered. I don't know if I explained.
But the free spinner, now I remember, the free spinner, you discussed it for the square well system, right?
Yeah.
Okay, so you say even at the highest theta, I am not 100% covered, and it is those teeny tiny regions that are unpatched that make the whole difference. Okay, no, that seems.
And then the thing, for example, in the small patches, is that the particle get like stuck with one of the bonds, and then it starts spinning there without actually moving, decorrelating, and something that you don't see when the system is more or less well covered, because it keeps on exploring all the orientations and everything without having to break the bonds. But then in the other case, it has to actually break the bond to decorrelate. So it keeps on spinning until some other particle gives a kick or something to break that bond.
Okay, so then I have a question on equation 6.5. This is the tetrahedrality, blah, blah,
The
blah.
collapse.
The collapse, yes, that puzzled me a lot.
Yes.
And you were so cautious that you didn't put it in your presentation.
Yes, of course.
Why?
Well, the thing is that we did the collapse not as a kind of explanation or as a way of relating with the theory. It was just more like okay, we can collapse all our data, and actually it has a functionality which resembles a little bit about the things that we would find in the Adams-Gibbs theory or something like that. So it has more or less the same functionality, but then the things are a little bit puzzling in general in there. And the thing that jumps more for me is this critical eta. So in theory, with this collapse that we use, the critical eta is universal for all compositions and all mixtures, which for me it is completely not true, because the thing is that depending quite a lot of the size ratio, and as we have seen, the dynamics are really different, and for size ratios which are larger, like they are shorter, the particles keep on diffusing and there's no problem, and we can actually, in this collapse, I took a critical eta of 0.598, and I could actually keep on equilibrating systems further than this critical eta. So the sense of a universal critical eta for everything, for me, it was the first sign of saying, okay, this is just an artifact to see that everything collapses. And if in some sense we would like to have a universal kind of function that has captures all the data, we could have this. But exactly how physical it is not really, yeah, it is not directly physical.
So perhaps another way to tackle this issue is to have a look also at your prefactor tau naught, because I don't know if people can follow this discussion, which it's a bit of a private discussion. We are speaking about putting together all the data in the left plot that we're taking for different volume fractions in a sort of universal plot where the dynamics would be fitted with a Vogelfulcher like divergence of the relaxation time, but where the variable on the x-axis would be directly related to the tetrahedrality.
Yeah.
And when you do so, you basically fit your data on the left-hand side, and in your fitting, among your fitting parameters, you have some characteristic time scale, which in a usual VFT-like stuff would be typically a microscopic time scale. And so there would be no reason that this, the whole point is that this microscopic timescale does not depend on volume fraction, because it's inherent to the size of the particles, for example, in colloids or stuff like that. So to me, having a tau naught that depends on volume fraction doesn't make much sense. But then I would like to know how much it depends on volume fraction, because that information was not given in the thesis.
Yeah. Oh, and I actually did calculate it, of course, and I don't remember exactly how was the relation. Yeah, I don't remember actually how was the relation with the tau 0 and the eta. I kind of think that it grew with the packing fraction, but I don't really remember the details.
Okay, so but I guess that my point is that if tau naught has a mild dependence on volume fraction, then perhaps it's worthwhile scratching one's head and trying to figure out whether that sort of super scaling makes sense and what it implies and so forth.
But
If tau naught depends a lot on volume fraction, then to me this is okay. It's a nice graph, but nothing really deeper than that.
Yeah, because the problem that I actually remember is that it really depended of eta. It wasn't not just a mild dependence. It was a really dependence. More when I was going to higher packing fractions, then the dependence was completely different from the one of lower packing fractions. So that was the reason we actually use it as a function of eta.
Okay.
Yeah. So yeah, the thing with this collapse in general is a little bit hard because we are having like so many different compositions and so many different size ratios, which at the end we could try to, for example, if it depends of the size of the particles or something like that, I would expect, for example, that it is not again to be completely general to all the different size ratios and composition, to this wide variety of different systems. So that's that's something that it should be taken really careful, and in general the collapse should be taken really carefully because it is not really showing something quite physical. So yeah, it is just one way of collapsing all the data, but then exactly the meaning is not not directly.
Again, I think that this is a very interesting notion of tetrahedrality, and perhaps it would be worthwhile checking a bit more in detail how things depend on volume fraction for a given system composition, and try that for several system composition, because at the end, volume fraction is typically the control parameter for these systems. So learning how
exactly it depends.
Exactly, how things work when you change volume fraction for a given system composition, that I think would be very interesting.
Yeah.
So, Emmanuel, do I still have room for a couple of quick questions on machine learning?
Yeah, sure.
Okay, thanks. So can you go to your slide 32 for a second?
Yes. Yeah, here it is.
Okay, so if I got it right, you're saying, cool. I can say something about these two populations of particles starting from one snapshot.
Yep.
But the one snapshot is the one snapshot of propensity, right?
So no, it's just the one snapshot with the position of the particles. So yeah, of course, the one of the propensity. So for example, but I could take, for example, any snapshot. I train my machine learning algorithm, and with that, I can apply it for another snapshot. For example, in here, I had this snapshot for the propensity. I applied the machine learning, and then I found the probability of being, prone to rearrange or not. So yeah.
Okay, but when you do the training, of course, you need the dynamics over an extended period of time, because that's the way you calculate the propensity, right?
Yeah, well, for the propensity, but the thing is that they are separated things. So for the training of the machine learning, I just need the positions of the particles. I don't need any information about dynamics, any at all. Then just for like approving if it was actually well capturing the regions that are going to be related with the propensity, then I calculate the propensity, but in a separate way, not related with the machine learning. And then I did exactly that. I have one configuration. I started, I don't know, it was like 32 different simulations with the same initial configuration, change the velocities according to a random Boltzmann distribution. And with that, I get the propensity. But it is just a calculation which is not related to the machine learning. To the machine learning, it's just the structure of the system that it is needed.
Okay, yeah, that clarifies things for me, thanks. So I guess that my last question or remark about the machine learning thing is that I guess that many people have the same comment, that it is nice. You can divide your spheres in whitish spheres and reddish spheres, fine. But then I guess that one would really, in principle, like to learn something a bit deeper in sense of what makes a reddish sphere reddish, or probably more likely, what is the structural information that is most relevant. I mean, you have done this work for some systems with your tetrahedrality. You say, okay, when I cannot just guess in advance what would be the relevant structure, then I do the machine learning stuff. But then I suppose that one has to go back once he got the results from the machine learning algorithm and ask the question, okay, what are those structural features that make the regions belong to one class or the other class, and so forth. Can you understand anything of that with your machine learning results?
So just with the machine learning, it is hard to say exactly which is the cluster that is going to be involved. We can just know how to distinguish them. But then after that, once we have the probability of being in one of the family or in the other family, we use the topological cluster classification to see which are the clusters that are going to be related to these red regions and which ones are going to be with these white regions. So we did it for the Wanstrom and the Cobb-Anderson, the ones that I show in here. So for example, the white regions were the ones that were related to not a big movement. The red ones were prone to rearrange. So for the ones that are not going to move, we are actually capturing more or less the same clusters that the tetrahedrality was capturing. So for example, we have the Dicosata cluster, we have the defective Dicosata cluster, and then we have quite a variety of different families, which there are different clusters that can be decomposed in this tetrahedron. So actually in the Wanstrom is capturing more or less the same type of structures that the tetrahedrality was capturing. In the sense of the regions that are prone to rearrange, we found that they are more correlated with these clusters that have one or more square pyramidal subclusters. So yeah, so for example, the BCC, it was also correlated to these regions that are going to actually move or not to move. And then in the Cobb-Anderson, the things are a little bit harder and they are not that clear. But then in general, we were more or less capturing the same behavior. So we are capturing a wide variety of different clusters with different characteristics and everything, that they were more related to the regions that are not going to be prone to rearrange. So in general, the tetrahedrality and the Wanstrom and the machine learning, it's capturing the regions that are not going to move. They are the well-packed. They have more tetrahedrons and they have like more these icosahedron clusters and everything. So in principle, after doing the machine learning, we could use, for example, the topological cluster classification, or we could use I don't know, maybe a Voronoi construction or something to see which are the clusters that the machine learning is capturing. But just with the machine learning, we don't know exactly which are the clusters that are going to be related. We have to do some other studies additional to actually characterize quite well the clusters.
Okay, well, thanks a lot, Susana. Again, congratulations.
Thanks.
And give back the mic to Emmanuel.
Thank you, Luca. The next examiner is then Marjolaine. So it's up to you, Marjolaine.
Yeah, thank you very much. Yeah, first of all, congratulations with a very nice thesis. I read it with very much interest, and I also learned a lot of it. Yeah, let's immediately jump into the questions. There were already many questions that were already asked, but perhaps I can just continue on the discussion. So about the Cobb-Anderson mixture, because you have the slide here.
Yes.
So you didn't see a very strong correlation between the dynamic propensity and the icosahedral clusters and the tetrahedrality. And that's why you use machine learning to understand better what are the local favorite structures.
Yes.
But also from here, if I look at this plot, this machine learning plot, there's still not a very strong correlation. So this plot was not in the thesis, so I have to reformulate my question now.
Yeah.
so does that mean that the TCC doesn't capture the important clusters of the Cobb-Anderson mixture?
Yeah,
different ones.
So the thing is, with Cobb-Anderson, it is in general, I think it's a little complicated class former because of the non-additivity. So in some sense, it might be that the TCC is not capturing all the local favor structures. That might be. Also, I did in a site, for example, I tried to look for simple clusters and see how these were correlated with the propensity. And either the simple ones that were like done by square parameters of clusters and everything, they weren't really correlated with the propensity. And the other thing is that it might be that, for example, in Cobb-Anderson, we are seeing everything really local structure, only the first neighbors, and we are not really taking into account the other environment of the system. So it might be that Cobb-Anderson needs a little bit more information of I don't know, probably the second neighbors or more complicated and more not that local structures. So that might be my guess, that maybe the Cobb-Anderson needs a little bit more information to capture the structures that are related with dynamics. So
is there a way, or did you think of trying to calculate the free energy of the local favorite structures? There was a paper, for instance, by Paddy Royale, where they did it using
so for example,
approach.
Here in the TCC, they have, for example, all the clusters that have a K in here, the 13K, the 9K, they are the clusters that correspond to the ones that have the minimum energy for the Cobb-Anderson, which were calculated by Paddy Royal, and they fit them in the TCC. But even so, they are the ones that have the local, the minimum energy for the Cobb-Anderson. They are not really well correlated with the propensity. So that's the reason I was thinking, well, maybe we need a little bit a bigger picture of the structure in the Cobb-Anderson. It might be that it is the case.
Yeah. Yeah, the machine learning, it's similar to what Luca already stated. It looks a bit as a black box. So you feed in an input, many features, and then something comes out. So you use a dimensionality reduction method to group it in two groups. But yeah, in the end, you actually like to learn something from it. Did you try to use simpler dimensionality reduction methods, like just a linear dimensionality reduction method, because then you still know what you plot on the axis, like principal component analysis? Or did you also try, for instance, a feature importance analysis on your, so just to see which features are the important ones to group the two groups?
Yeah, so I didn't really try other methods actually. So, but for example, one thing that we saw, well, this was after that we calculate with the TCC, and so which are the clusters that were more related, but also we could calculate, for example, the average value of the bond order parameters per different types of families, and then from there to get some information about if there was a bond order parameter that was more relevant to other, and how this was related to I don't know, symmetry of the cluster. But for example, only the ones that I can recall now that had a slight difference, but it wasn't a really big difference in the one strom. It was, for example, Q6, the bond order parameter, but it was a really slight difference. It wasn't really like a huge difference between these two. So at least from just the average value of the bond order parameter. So for example, just that, I don't think we can recover that many information about what is the exactly type of structure that the machine learning is capturing. I think in that case, we have to do some a posteriori analysis like this TCC, and then from there learning like a little bit backwards. So,
yeah. But you didn't try to correlate, so what you plot in the end in the 2D plane with the TCC clusters, so where they would fall in this projected plane projection. Okay, then also again on the collapse of all your data, it's page 87. I don't know on your slide.
Yes.
What puzzled me is that previous experiments and simulation studies, they showed actually an algebraic NCT divergence with a critical packing fraction of 0.58, and then at higher packing fraction in exponential VFT focal Taman divergence with a critical packing fraction of 0.64. And now you fit it with a focal Taman exponential fit, but with a packing fraction that is very low.
Yeah, yeah.
So
yeah, so mainly here it was an artifact that we use for actually collapsing all the data. And the thing is that, for example, at least low packing fractions, low packing fractions, but also in the high packing fractions, we start seeing some deviations. So it is not really, in some point, this collapse and this all this relation that we have, it breaks at higher packing fractions. For example, for even a higher packing fraction of 0.59 or something, for the binary mixtures, I missed this nice collapse. But then, for example, for the polysperse systems, is something that has been in my mind. I still equilibrating some higher polysperse systems up to, I think it was a packing fraction of 0.61, 0.65, I think, 605. Things were actually collapsing quite well with the both collapse with the one of the only the tau d as a function of the number of the tetrahedra, and also they were collapsing quite well with the PFT type of equation. So for me, it also puzzles me a little bit because this MCT packing fraction, I'm not so sure, for example, if it should be a little bit dependent of the morphology of the system, if it should be dependent of the size ratio and the composition, or it should be a MCT packing fraction that it should be general and universal for all the hard spheres. So after seeing how the dynamics behaves with different size ratio and compositions, for me, it is a little bit weird that there's just one packing fraction that should be taken for all of them. And it's a problem at the end of the collapse that it has just one critical packing fraction, which it doesn't really make sense by just seeing that the dynamics, it really changes and that we can push some systems really deep into higher packing fractions without seeing any different behavior of the dynamics or the decay of the intermediate scattering function. So
yeah. No, interesting. So it's, yeah, I think it needs further investigation.
Yeah.
Yes, so the general gist of your thesis is that you try to look at local structure and how it is related to the dynamical heterogeneity and the slowing down in Glassy systems. And you find a very clear signature of the structure corresponding to the slowing down. But this also immediately begs the question, is there also a thermodynamic structure or is a signature of the glass transition or the slowing down? So did you try to look at it? Because structure is related to thermodynamics, so you can go from structure to thermodynamics.
So this is a quite a tricky aspect. We didn't actually see if it was quite related with the thermodynamics, but for example, things that have all already done regarding a little bit with this notion of the tetrahedron and how this is related with dynamics. So there was some papers some years ago, I think, that they also try to relate some differences of the tetrahedron as going deeper into the Glassy regime. And then they actually found that it was more or less related, and they could also relate it a little bit with more a thermodynamic sense. And they found, for example, that they would predict some changes in the, I think it was the entropy, and they did like a more extended work in the how and trying to relate to the actual class transition. But in here we didn't do something that we did, for example, to see if we are expecting a thermodynamic transition, if there was like a length scale, a growing length scale, and we didn't find a structural length scale that it was growing as accompanied by the dynamical correlation length. So that's the only thing that we checked. So I'm not so sure. Only by seeing this structure, I don't think we can have a lot of information about what is the nature of the thermodynamical class transition.
So did you try, for instance, to measure the pair correlation function for the different dynamical heterogeneities, so which are related to different structures?
So the thing I calculated, for example, the correlation length of the dynamical heterogeneity. I saw the normal growing and everything. And then I tried to calculate a similar correlation length for the structure, which if it is well related with the thermodynamical transition, I would expect that it would grow. But in that case, I didn't see like a growth of a static correlation length, which is
Yeah, I think the divergent length scale, or you try to calculate that in your appendix B.
Yeah, that's
figure B3. There was actually missing in what units you plot your correlation length.
True. Yeah, that's actually quite true.
So I was very intrigued by it, but it does only take psi 4.
Yeah,
it's not in what units, what your unit of length scale is.
Yeah, so
I missed the units at multiple places in your thesis.
Yeah. That's something I should deal with that. Yeah. So actually, even this structural correlation length that I calculated, I'm not fully sure that it is really well capturing the growth, because in general for these structural parameters, it was quite difficult to actually calculate the correlation length. So, for example, in here, I tried to do like this 2-point tetrahedral correlation function, like it is more or less based like in a radial distribution function. But then, for example, in there for doing the fitting, it was really hard to do the fitting, and it has a lot of noise. And then just by seeing the correlation, we can see that it is not really growing. And then the length of the units of the correlation length, I guess they are in units of sigma. Now all introduced units, I think.
Yeah, then it's extremely small, so it's not bigger than just the bulk correlation length of a dense fluid.
Yeah, that's a problem. And the same we saw with the machine learning. We didn't see like a growing correlation length in these structural regions that it's not really growing. So it keeps being a really open question if there's a structure that actually grows in correlation length by going deeper into the Glassy regime. It's still open, at least in this side.
So you also never saw any orthogonal behavior in your S of Ks, where there's a long wavelength divergence.
The problem in here, I try to see it, but because our systems are kind of small, so we have for the hard spheres, we have 700 particles, and then I simulated larger and larger, so up to 10,000 particles. Even so, it was quite hard to actually do the fitting of the structure factor, the Ornstein. So that's the reason I thought, okay, I cannot really extract some correlation length from them. Then let's try to do it in this way of doing with the radial distribution function, and then see if it is actually growing. And then but then it would be interesting. I'm not really expecting that it's going to grow, but it would be interesting to do bigger sizes of systems, and then see and do a proper fitting and see if it's going to grow. But I don't really expect that it will grow.
Yeah. So then, yeah, just to, because you have a very nice introduction on the various approaches for glasses. MCT, but also other theories. Also there you discuss, for instance, the configurational entropy, but also the number of free energy minima. Can you now relate what you find, because you try to connect the dynamic heterogeneities to structural heterogeneities in your system? Is now the mechanism behind these structural heterogeneities, are they entropic of origin, or is there an underlying phase transition, or is it energetic? Can you say something? Because I think you must be able to calculate the free energies of these different structures now in your glasses.
So we didn't really calculate any of the free energies. For example, I just followed that they were like the local free energy minimum of the different potentials, but then I didn't really calculate them. And then something that I have been, a clear answer about how to relate this with the configurational entropy, I don't really have. But then in some sense, I can imagine that it is going to be well correlated at the end with the entropy. A good relation, I don't have it, and we didn't really calculate, and we didn't really go that much into the theories. So it's something I don't really know, but because these tetraederate are getting better and better packed, I guess it might be well correlated with the configurational entropy at the end, and we could see something nice in there. But it is something that we should see in some future.
Yeah. Yeah, I have many more questions, but perhaps I will give the word back to the president.
Thank you, Marjolein. Next, we have Kirsten Martens, next examiner. So please, Kirsten, it's up to you.
Yes. Hello. Thank you, Emmanuel. Let me start with some comments on your thesis work, or also about the present situation first. I think it's a true pity that we are not all together, and we are lacking a lot of interactions that should have been there. And well, it's a pity for us, of course, for the jury, but especially for you. You did a lot of hard work, commitment and persistence, and this during a time which was even more difficult to do a PhD thesis. So you should have this moment of, it was said, it's a bit like a celebration of a wedding usually. So I hope that later on at some point it will be possible for you to really celebrate these things. And I want to congratulate also on the manuscript. So this week was a little bit difficult for me because I'm a member of 3 juries this week. And so I had a lot to read, and I was very happy to find, well, you did a work which includes enormous amount of parameters. So you have the patch size, the number of patches, and then the particle sizes. Then you have the composition, aspect of the sizes, and then the polydispersity. Everything is there. So there are a lot of parameters, and this can lead to a huge PhD manuscript in principle. But you did something very good, which is to concentrate on the most important parameters. And this is, for me, is really a sign of the quality of this thesis, because you could extract what are the relevant control parameters. And you did a presentation of this, which is very concise, well written, and right to the point. And so it was a big pleasure to read this, and I learned a lot. I learned a lot also because probably I'm also one of the further person in the community here in terms of subject. I have never worked on glassy dynamics. But of course, I'm following this subject. So it's also a little bit hard for me to formulate new questions after this set of questions that have been done already, but I will try. So my first question is related to, well, you're now expert on local structures, and you know a lot about how different potentials will create different structures. And I would like to know whether you have a sort of recipe or an idea about the minimal ingredients for the potential to produce this tetrahedral structure as the most, well, you mentioned that it should be repulsive. Is that the most important part?
So I think the important things, well, it is, well, we can see, for example, from the hard spheres, we have only repulsion interactions. So that's something that we have seen, that icosahedral are well there, and also the defective. But then we can have, for example, the one-strom. The one-strom, it also has a repulsive interaction, and it also have this icosahedral type of cluster. But also, there have been some metallic glass formers that they have been shown that by going deeper into the glassy regime, the number of icosahedral clusters increases. And of course, in those type of metallic glasses, it's not only the repulsive part that it takes into account. So I guess, and also by seeing the Cobb-Anderson, and also because I did a small, I played a little bit with some non-additive hard spheres, I can imagine that if we have a additive interaction, and if we have the repulsive part, of course, then it is quite likely that we are going to find icosahedral clusters. So, but then in the moment that we have the non-additiveness, then we start messing up a little bit with the local favor structure, and then we start having other types of different local favor structures. So yeah, I would say that mainly that.
Okay. And then my next question is also about the parameters that you choose to study. So it was already said it's a bit of a pity that you didn't look at the packing fraction in the case, but of course you looked at everything else. So how can you criticize? So, but then in the case of the patchy colloids, and also in the soft particle studies, you're looking at the effect of temperature.
Yeah. And
you choose to compare the dynamics at a given temperature. And so my question is, you could have also chosen another state and phase to compare with, for example, at the same potential energy. And I was wondering whether you have...
So actually we didn't compare with other things, but for example, something that there has been some comparisons, and it's some parameter that it is well used. It is the same amount of, for example, the relaxation time of the diffusion time. So by having a fixed diffusion coefficient or a fixed relaxation time, that could also give me a good comparison, because in that point, I would expect that I'm comparing exactly the same, well, not exactly, or more roughly the same Glassy state. Mm-hmm. So for example, that's something important. But then in here now, just by thinking now at that, in here it would be a little bit different with the dynamics of the patchy particles. Because if I see, for example, for the patchy particles that are not the 10, 11, and 12, I can see that in general, the temperature was a really good comparison, because I can see that the diffusion and also relaxation time is mainly the same. They have in the same order and everything. But then once icosahedral clusters kick in, the relaxation time increases. And then I'm not so sure I would have these types of systems with the same amount of glassiness that I would find in the 12 patches, for example. So in there, it would be a little bit hard to compare to the same, the same slowdown. For example, in there, I wouldn't expect that it would be exactly the same. But for example, for the monospheres, which I didn't really talk in today, one way, for example, it was, where is it? Yeah, here it is. So I could compare, for example, for these two that I was using the 8 and the 12, and then I'm comparing different temperatures. And in here, for example, I can see that by fixing one temperature, the dynamics of these two is quite different. Actually, it is, for example, for these is one order of magnitude. But then I could find, for example, diffusion time, which is a fixed one. For example, I pick this one just to compare, and which corresponds to different temperatures. For the n equal to 8, it was a temperature 0.25, and for the 12, it was 0.35, and roughly it was the same diffusion. And then there, for example, I compared the structure of it to see if it was different, and this also gives me a better comparison in the same Glassy state. So if I would have to compare it in a different way than the temperature, I would pick, for example, the diffusion or the relaxation.
And for that, if you choose in that example the same diffusion, how do the structure compare?
So for example, well, this is the particularity of the monospheres, which has been a little bit puzzling. Is that, for example, for the same diffusion coefficient, here it corresponds to the temperature of 0.35 and 0.25. So the first one in here is the 12, and the one below is the 8. And then I can see that in general, the structure is still being quite different. Even at the same diffusion coefficient, I can see for the 12 patches that the peak of the second peak is still splits. So I can see lots of icosahedral clusters. And then in the other one, I keep on having more or less like a high temperature liquid. So even at that diffusion coefficient, the structure is quite different from these two ones. two different type of systems. So,
and do these have also different glass temperatures, I would think?
Yeah, I could imagine that. Yeah, I could imagine, yes, because at the end the dynamics are different. So I can expect that it could change, and it would be also dependent of it. So for example, for the 12 patches, something that I show in the binary mixtures, the lowest temperature I could equilibrate, it was the 0.38. But it was particular to the 12 patches, because for the other ones, I could keep on equilibrating to even lower and lower temperatures. So for example, in there, I could imagine that the glass temperature, it is depending. For example, if you have more of these local Fabio structures, your glass temperature is going to be shifted to probably higher temperatures. So,
when you would look at the same distance to the glass temperature, would that maybe be also a relevant quantity?
Yeah, but in I guess yes, but I guess in some sense it would be, I could expect that it would be more or less the same of comparing the same amount of diffusion or the same amount of relaxation time, because they should be more or less at the same distance of the glass temperature.
Okay. Can you go to your slide 27?
Sure. Yeah, here it is.
Yes, again, here also my question is the different temperatures that you're studying there, how they are comparing to the glass temperature.
So that's a good question, and I should have the values of the temperatures of the Wanstrom and the Co-Anderson. Probably I have them just at the bottom. The Co-Anderson I don't really remember. No, yeah, the Co-Anderson is in here, is 0.42, and the Wanstrom is 0.65. Well, this is the MCT temperature, so we can take that. So for example, in the results that I show, let me go back. It's a little bit further. Yeah, so in Co-Anderson, we have a temperature 0.55, which is quite close to the one of the MCT. And also in the Wanstrom, we had a really low temperature for that system, which was 0.7, which is also quite close to the MCT temperature. So I guess in this case, we can more or less compare, not like you say, not exactly with temperature, but how close they are to the MCT temperature. And for example, I guess that these two red lines, they are quite really similar in terms of dynamics and in terms of being closer to the MCT temperature. So,
okay.
Yeah.
Then my question is, what happens if you go in the glassy phase? Can you still use these structures below TG to have predictions about the aging mechanism?
I'm not really sure that they are going to be still relevant, because, for example, it has been shown that in some point things saturate, for example, a little bit, and also because of the definition of the local Fabio structure in the Dicosata cluster, in some point it will saturate the system and it cannot grow anymore because it cannot tile the entire space. So I guess that by going and entering in the glassy, in the glass, below the glass temperature, I would expect that I cannot really know a lot of things by the structure. I think in there things really start changing, and probably the structure is not the better thing to see in below the TG. And well, we can see that reflected on all the theories and everything, that things start really changing below the temperature of the glass transition. So I wouldn't really expect that the structure will have a big effect there.
I'm asking that question because when you look at sheared systems, it has been shown that structural quantities still, if the glass is poorly aged, it has been shown that the structural quantities can quite well predict where shear transformation zones will happen. Whereas when you are deep in the glass and you have a well-relaxed glass, then the structural quantities do not do as well.
Oh, okay.
I wanted to know whether you have some opinion about that.
So actually, well, we have started checking what happened with shearing about this tetrahedrality and how well it works. And for example, actually in there we are using the shear. So in inherent structure, so it is in the glass phase. And in there we have actually seen that, for example, the tetrahedrality, it really changes, and it is a little bit sensitive, for example, for the different types of shearing. And we have actually, for example, above yielding, where we have the shear band, where there's this region that it will keep on having some diffusion. We have seen that, for example, the tetrahedrality is actually capable of predicting or capturing where is going to be this shear band and where is going to be the regions that have, that they are completely blocked in there in the local
it is going to predict from the initial state, or it's going to predict the fact that the shear band is there?
So we would really like to know, and we would really like to see if, from the very first that we are able to predict the shear band, but so far we haven't been able to do that.
But yeah, what you're saying is that when the shear band is forming, you see this in the structure. Yes.
Yeah, yes. That's it. Once the shear band is formed, I can see the differences in the structure.
This has been shown also already by papers, Emanuela Delgado group on the icosahedra. Yes. Mm-hmm. So, one of my questions is then, would it be possible to use these structures to somehow define a local age, do you think?
That's actually something that I haven't really thought about, and I am not really expert in all the process of aging, so I'm not really sure how to. Yeah, I don't really know, but it might be interesting to see.
Then I also had some question about the 4-point correlations. In your manuscript, you're showing this for the hard spheres, but I guess you have done this study also for the other systems, for the soft.
So actually, the dynamical correlation length, I did it only for the hard spheres. I didn't do it for the one-strom or the Cobb-Anderson. The only thing that we did, for example, in there we calculate the dynamical correlation length, and then we calculate also the static in the hard spheres. Well, we try to calculate the static. And for the one-strom and for the Cobb-Anderson, the thing that we calculated, and probably I don't have the images in here, is the correlation. The static correlation length, we try to extract a static correlation length for the one-strom and the Cobb-Anderson. But then at the end, it has a weird shape of decay. So it wasn't really easy to have a nice fit to extract a nice correlation. But then at the end, we saw that, for example, we didn't have any growing of the static correlation length. And then for the dynamic correlation length, I think it will have this normal growth that it is expected in the Glassy region.
Okay. And I have some more questions about the machine learning. As everyone else, one is a little bit frustrated, right? Because it's doing well, but you want to understand something from it. And so I didn't understand 100% the answer to Luca that you gave. You were saying that it can help to find the clusters that are involved. And my question is just, is there some advantage on doing rather the machine learning instead of just looking at the propensity and looking at the structures with Voronoi methods where the propensity is high? What is the difference?
Yeah, so the thing with the good thing with the machine learning is that, for example, in the other ones, we have to calculate the propensity, we have to do the simulations, we have to restart the simulation several times, and at the end, that costs us some computational time and at the same as some work. And the really big advantage with the machine learning, it is that we don't need anything about that. We just need a snapshot with the positions of the particles.
Once it has been trained, right? The training is not as costly.
So the train, we can do it just with those positions. We don't need any information about the dynamics. That's the main advantage of the unsupervised machine learning. So once we have the snapshot with the positions, we calculate the bond order parameters. We can train this neural network to recover again the bond order parameters, and from there once we remove the part of the decoder, we can classify the particles. So in general, it is just a classification according to the structure. So it is just going to capture the particles that are going to be embedded in a different structural environment. But it seems that these different structural environments are correlated with the dynamics. So even if we don't know anything about the dynamics, we could more or less know just by knowing, for example, just by seeing the right picture, okay, there are going to be some red regions, so I could expect that they are going to be proner to rearrange without actually knowing if they are going to rearrange or not. So that's
I understand
the main
point,
advantage.
but from a practical reason, from a practical standpoint, is it faster? Let's say, if I give you the problem and you have the choice to do either the dynamics or train your network, which one would be less
costly? Yeah.
costly?
So something that I didn't mention is that this is extremely fast and extremely efficient. So yeah, training the neural network and everything, it would cost less than 5 minutes. So it is something really, really fast. And for example, calculating the propensity depending of the system, depending of the size of the system, it could take at least 1 week or something like that. So in terms of efficiency, it is it has a really well performance. So that's a good thing.
And then another question that came to my mind, would there be a way to use the machine learning methods to find a quantity that would give a growing correlation length?
So that would be really nice. And I'm not so sure how to do exactly. And it would really give a lot of answers, because if we manage to capture something that actually grows accordingly to the structure, that could shed really a lot of light in terms of if it is like a thermodynamic glass transition, of what exactly is happening there. But then exactly, I don't know if we could search for something that will grow. It would be a matter of exploring, for example, I don't know, probably a wider range of local environment and see if there are some changes in there. But I don't really know. And it would be really nice if someone managed to find this growing correlation length. That would be really nice. Then I'm not really expecting that it really grows. I don't think it will grow.
Then I have a more informal question. I would like to know what was the most enjoyable part of your PhD thesis, and when you started to look at the tetrahedral configurations, what was the initial goal, and did you expect already that this would be the outcome?
So I don't know. That's a tricky question, actually, because I really enjoy everything. I really enjoy my PhD. It's something I'm really happy and I'm really proud about, because I really enjoy the PhD. The 3 years, I really enjoy them. I think once we found the tetrahedrality, I was really happy and really impressed. And of course, all the process of publishing and everything, it has give me ups and downs, like having the reports, and then the reports are nice, not nice, and then all those things are new to me and they are really interesting, and I have learn to enjoy them. So that has been quite good. And also, of course, this unsupervised machine learning, I was quite eager to learn, because nowadays we hear that they use machine learning for everything, and in every field they are using machine learning. So I was really eager to learn that. So this has been really nice. And then in the second question about the tetrahedrality, so our main idea, it was to see, once we have the directionality, we can see that we can enhance icosahedral clusters. So we started thinking, if by playing a little bit with the size distribution of hard spheres, we would have a region where we could enhance these icosahedral clusters. If we could control the dynamics only by having just isotropic interactions. So that was the first ideas that we started developing in there. And then, well, we saw that effectively there were some regions with higher icosahedral clusters than others, and it was really nice. But then in there, we started thinking, okay, maybe it's not just the icosahedral cluster, maybe there's something else. And then from there, we started looking to other structures that would capture the dynamics. And then I found that these big different clusters, they were all correlated. And I was just checking each of them and see which ones were the best ones. And then we started seeing some similarities in these different clusters. So they have a ring of 5 particles in the center. So from there and from the other works and everything, we said, okay, we can decompose actually quite well all of these clusters in the smallest, and then from there the idea of calculating the tetradrality and see. And then it was really nice to see all the collapse and the data we saw. The day that we saw the 2 graphs of the diffusion time and the tetradrality, it was like, oh, it's really working. It's really nice. So that was really nice.
Yes, I have finished my question. Give to the next person.
Thank you, Kirsten. So maybe I will now ask mine and then give the word to the advisors in the end. So like I said, I mean, I really enjoyed reading your manuscript and being there for the talk. And one of my first reactions when I received it and I started to read was, how come this was not done before? So it's not a criticism, of course, it's quite the opposite. It means that you are touching at something quite fundamental. And in addition to this, you have very, very interesting results. And I think some of them will stand in time. This tetrahedrality thing is a strong result, quite obviously. So I like the inventivity of this work. You have a very nice model system. This patchy thing turns out to be quite a fantastic tool, and you really made the most out of it. So for all this, for the quality of the results, for their soundness, and the way you executed the analysis, I think you should really be commended. Now, I have a few questions, of course. Some of them were raised already, of course, the connection to thermodynamics, a growing length scale, or the fact that it seems more difficult to make an orientational glass than, let's say, a positional glass. Okay, so I will leave that aside. I note in passing that there is a funny typo in the text, which is somehow maybe glass related, like you are expecting very long time scales, but the 50,000 years to date back to the Egyptians is maybe a bit too long, right? Maybe,
yeah.
Something like an order of magnitude. Okay. I was actually, so there is one important substance which likes tetrahedra as well, and that is water. So do you have something to say about possible glassiness of water in light of your work?
Okay, yeah, that's actually, that's interesting. And I haven't really thought about that. I have more or less started, but I haven't really thought about how this could apply to water, because the thing is that in general, all the behavior in water is quite different, and it has different behaviors. And then there's this liquid-liquid phase coexistence and everything. So I don't know exactly if, for example, if we could apply the same tetradrality in there, and if we could see something, because at the end in there we are expecting that most of the local favor structures and everything there can be decomposed in tetrahedron, and then I'm not so sure if we can find with the tetradrality actually find different types of regions with different amount of tetrahedron. So that I'm not so sure. And then in the sense of machine learning, I have seen that, for example, there have been lots of now improvements of machine learning and trying to use this type of unsupervised, well, not exactly this type, but some unsupervised machine learning and different tools to actually more or less know a little bit and have more insight about water. But then exactly the tetradrality, I'm not so sure exactly how to apply it. And also, of course, there have been some models about using patchy particles to try to model the water. So that's one of also the nice things of patchy particles, that they can reproduce a little bit how is the phase behavior and things like that of these type of molecules that have a particular number of valence. But then, yeah, for the tetradrality, I'm not so sure how to explain there, because I could imagine it is not going to work really well, because the favor structure and the structure that we can find in the water are really similar. And I'm not so sure if it would capture the differences between these two types of local favor structure of the water. So, yeah.
Okay, maybe now a somewhat technical question on the way you define the tetrahedrality. So you make this Voronoi construction. Then what is the tolerance you use for, let's say, fluctuations in the positions of the neighbors?
Yeah, so actually this is all based in the Voronoi construction of the TCC. So in there, so that's one of the advantages in there is they take into account a little bit about these thermal fluctuations. So for example, they do two main modifications. The first one is they prevent to count the particles in the second shell. So they say that, for example, two particles are going to be neighbors only if the line that joins them passes through one of the faces. So with this, we get rid of the second shell, and then we take into account more or less the thermal fluctuations with having just the direct neighbors. And then another thing that that introduces a parameter that allows that, for example, if we have 4 particles like this one, how much they can be distorted to be counted like 4 or just 3. So this in some sense is going to affect a little bit the tetradrality, because if we we allow these 4 particles to actually distort quite a lot, we're not going to see, well, we are going to see the tetrahedra, but we are not going to see if there's, for example, one particle above or below.
So is it critical to choose well those little parameters that are going to quantify the tolerance to fluctuations?
So it affects a little bit. And for example, in here, the parameter that we use is 0.82, that it has been shown that it is good for Dicosata cluster. But then I have just recently started playing a little bit with this parameter to see how things change. And then, for example, if I have a normal Voronoi construction without this allow the distortion of the 4-member ring, I can see that all my data are a little bit shifted to larger values of the tetrahedral. So it is actually a little bit dependent of these parameters. So it's something that it should be taken a little bit careful. And then, well, we just defined that the tetrahedra is going to be just the 4 particles that they have, they are all linked all together by, as they are neighbors. So this is the main definition that we do as a tetrahedron.
Okay. So, well, I guess mode coupling theory people are quite happy with what you do, because basically it gives them, well, sound basis for their approach. Now, do you have something more to tell them, like because they take as an input the structural information to derive the dynamical quantities? Do you have some advice on to reshape the theory?
Yeah, so actually, for example, I have been, because I remember once I have a question quite similar to that and saying, well, okay, in the MCT, I have just the structure factor. Is this capturing actually all the tetradrality and everything? So just by playing a little bit, I was playing with the structure factor with the first peak, and I was trying to see if it was actually quite, it was capable of capturing all these changes on dynamics and the changes in the tetradrality. And for example, just by knowing the value of the peak of the structure factor, it wasn't really changing, and it wasn't really capturing all the changes on dynamics and the changes on the structure of the tetradrality. And also, I started playing a little bit with the width of the first peak and everything, and I didn't find anything quite conclusive. So for reshape a little bit, I don't know exactly how, and it would be really interesting if in the MCT and if with the structure factor, in the information of the structure factor, we could add a little bit of information about how well packed are the particles, which at the end, it more or less it should be, the information should be in the first peak, but I'm not so sure if there should be, there must be a way of introducing this as an input to the MCT and actually making it a little bit better. However, the MCT works quite well for predicting a lots of things, and I think it might be just the case of modifying it a little bit for temperatures below the MCT, and in there I am not so sure how things would work.
Okay. Now, concerning the bond order parameters which you use, it seems you define them from a distance criterion, while I would have expected that maybe a Voronoi construction might be a better way to do.
Yeah, so for example, I use in the whole thesis, I use the bond order parameters several times. So for example, at the beginning, I in the patchy particle systems, I use them, the bond order parameters, and in there I use just the distance criterion, because we were just mainly exploring what was the changes in the structure and everything. But then, of course, a more refined study would be with having the Voronoi construction. And then for the machine learning, we use again the bond order parameters, but in there we didn't use just the cutoff. We use another way of defining the neighbors, which is the solid angle neighbor based. So in there is like a more or less based in a Voronoi construction, and it is not just the cutoff there. So to do it a little bit more refined, because at the end it's something that we should be careful to not to take into account other types of neighbors and things like that.
Okay. Also, you talk from place to place about the breakdown of Stokes-Einstein relation. What would be the mechanisms behind this breakdown?
So, so the thing is that I could imagine that in the Stokes-Einstein, the thing is that the diffusion coefficient decorrelates from the relaxation time, and in some sense, the diffusion is still even if even if the particles hasn't really moved to other, they are hoping, and then they are starting to diffuse something that it might be not really captured by the relaxation time. And in here in the patchy particles, at the end, almost all the Glassy systems, they have this breakdown of the Stokes-Einstein. So I was really expecting that it was going to also break.
What do you really call the breakdown? Because maybe the viscosity, or at least the friction, is defined the wrong way. So maybe they still hold, but we are using too simple an approximation for the friction. Or this is what I like to understand better.
Yeah, that's actually something that it should be taken really carefully, because the thing is that we're defining the packing fraction, the viscosity, we're relating it quite directly to the relaxation time. With this model that I said, like the Maxwell model and everything, and we're just saying, okay, we can relate it, and then with this we can define all the Stokes-Einstein and everything. But then it has been shown that it shouldn't change that much, and we should correlate well the viscosity with the relaxation time. However, I'm not so sure if there have been like really detailed studies about if this breaks in the Glassy regime and how this approximation really worked well. And this is something that I think it should be filled up to, because I have seen lots of studies using viscosity and some others using relaxation time. So it should be, I don't know, I guess someone should do a really careful study about the relation between the viscosity and the relaxation time at the end. Mm-hmm. So in here, I use the relaxation time. I didn't calculate the viscosity, but of course, there's always the doubt of it is well defined, or is it not really well defined.
There is one line in the manuscript where you mentioned that there is a way to bias the system towards the formation of specific structures in molecular dynamics. So of course, it's a mathematical trick, which you have good reasons for not doing it. But what is this trick? Well,
so for example, in there, I remember it was mainly for the monosparse systems that one way of avoiding crystallization is by enhancing these type of structures, or by trying to avoid crystallization. So I remember that they modify the potential such that it is actually enhancing a tetrahedral order. So they are adding, what was they are adding? They were adding some term in the potential, so they were avoiding crystallization. But then the main modifications, they should be in the potential. And then by changing the potential, of course, by doing the molecular dynamics, we're going to change things. Yeah, but it wasn't really the molecular dynamics. It was more the potential that it is changed.
Okay, yes, something also I'd like to ask to have your vision on is this non-monotonicity of the diffusion coefficient, which you show in your, let's say, I think it's page 37. So you'd say that you have a competition between two types of glasses at low temperature or at high temperature. What's the hand-waving way to understand this non-monotonicity?
Is it the one that it is related with the, I think it is mainly because of the reentrance. No, yes, I think it was because of the reentrance.
I guess my question is on the reentrance.
Yeah. So, so the thing in there in the reentrance is because at the really low temperatures, everything is going to be driven by the attractions of the patchy particles. So once we start increasing the temperature, of course, the particles have more kinetic energy. They start diffusing a little bit and having some diffusion. And then when I go to even higher temperatures, the things start behaving like hard spheres, and once more, everything is arrested. And then the thing is that we saw exactly the same things with the patchy particles. And I guess, I don't know if the comment is more or less related with the rotations, because I said that in there, there's a breakdown a little bit weird, because we are expecting that the Stokes-Einstein divide also breaks. But in here, we have a really weird breakdown because the reentrance kicks in. So we have this different behavior of the relaxation time with the temperature. We have the reentrance. And then also we have the effect of the temperature in the rotational dynamics. So I don't know if it was related with that mainly.
And what about the difference between the hard sphere limit and the square well? How can you understand that you have a larger diffusion for the square well?
So in the square well, well, I guess in the square well at the end, these attractions, they are going to making some particles to attract better and leave some free spaces to the particle actually diffuse. Mm-hmm. So I think in general, this, and it is mainly because of these short attractions, that some of the particles are going to tend to be closer to other because of the attraction, and they're going to leave some free spaces, and then the diffusion is going to be easier for the particles to decorrelate. And then in the hard spheres, we don't find these attractions, and then the particles, they just get trapped in these structures of really well packed.
Okay, maybe one last question. You have learned quite a lot on structural glasses. Now, do you have something to say to spin glass people?
Yeah, so the spin glasses, I have just recently checked because it's not really something I have studied, and I have just, in these couple of weeks, I started reading a little bit. And I don't really know a lot of things, but I was, for example, reading about this frustration, geometrical frustration in spin glasses. And sometimes this this geometrical frustration is due, for example, if we have a 3D spin glass that we have tetrahedrons, and then the spins cannot really align between them. And if you have more and more of this order in them, then you are introducing this geometrical frustration to the spin glasses. So for example, in there, it is something really new that I started thinking. I don't know if we could apply these terms of these ideas of the tetrahedrality for some 3D geometrical frustrated spin glasses if we have like this type of order. So that's something new, and it's something that I have just recently started checking if there were like some works going in the spin classes and everything. So it's an open world, I think, in there. So it would be interesting to also explore.
Okay, so I said it was the last, but actually maybe I will ask one more because yeah, it reminds me. What about 2D systems now? You have this nice understanding of the 3D problem. Is the geometry too plain in 2D to be really interesting and to lend itself to what you have done, or is there still some room?
So the thing is that the 2D systems are a little bit different because of the orders that you can have. It is harder to define the local Faber structure because then you have the exact order appearing there. So you have a lot of crystallization and everything. So for example, for the tetrahedral, it is really hard to put it in terms of the 2D. And that's the reason I said that what is next, because I would like, for example, to apply the machine learning to the 2D systems and actually see if we can manage to distinguish between these different structures in the 2D glasses, and which is going to be harder if we try to define a particular local Faber structure and see it from the 2D glass. It's going to be harder because of this, the crystallization and the order and everything, and it is harder. So I think, for example, in there's more room to do some machine learning and to apply those type of algorithms.
Okay, thank you. I am finished. So now you have 3 supervisors. I don't know how to dispatch the, should we start by, okay, Frank, maybe?
Sure. So I'm not actually sure how exactly I should approach this. Am I expected to ask questions or just provide some comments?
So I think I see Susana wave, no, please, no question.
But you can do
enough during the PhD, so I guess that's a fair answer. But you can deliver now what you never dared to say
No, I have nothing negative to say. Susana, I've had a great time working with you over the past 3 years. I've learned a lot, and a lot of that is due to your enthusiasm and willing to try new analysis methods and coming up with new ideas to look ways of looking at things, and new systems to explore. So I think you've done an excellent job, and you've put together a great thesis. So I will not torture you with questions at this time, but I want to thank you for all of your efforts over the past 3 years. And I think we've made some serious dents into at least our understanding of the relationship between structure and dynamics in these glassy systems. And I think that there's a lot to build on from there. And well, I'm sure we will keep in touch in the future, but these will be things that I will keep exploring as well. So thank you very much, and congratulations on a beautiful thesis. And then I will give the word to Giuseppe.
Thank you.
Okay, thank you, Frank. Maybe Rick wants to say something.
You're mute.
Yeah, sorry. Yeah, I have very little to add, just by congratulating you upon this beautiful work. My role has been a little bit more distant as a certified non-expert on glasses. So I actually have a few questions, but I don't think I will torture you with those. Maybe we can have a chat about those in the after party. So I think you did an amazing job, and I think I certainly learned a lot about these simulations that you did and the quantifiers that we defined and all that. So I think, yeah, with that, I would like to congratulate you and wish you all the best for your next phase in life in Utrecht. Okay.
Thank you.
Thank you, Rick. Giuseppe, yeah, some comments.
Myself, so I have a few notes, so I will be brief. So I would like, first of all, I'd like to thank the jury for having make this real, to be here, Emmanuel to be the chosen scapegoat, and the referee and the rapporteurs who have been really incredible, because you don't find often a referee that actually redo your simulation and check them, and all the other members for being so nice to be here and really open up a lot of direction that's really makes understand how much Susana has made into this work. Then I'd like to thank on another level CONACYT and Susana's family, Susana's university, to have nurtured such a very smart and round student that was handled to us for the last 3 years. And then finally, I'd like to move to Susana. So Susana actually arrived 3 years ago with her own money to our group, and we learned to work with her. And it was a special day for me today, because generally, I mean, student thinks that they are very nervous at their PhD defense, but I mean, personally, I'm really shitting my pants when one of my students is defending my thesis. And apart from the nightmare that both me and Susana had and shared this morning before the discussion, I actually was very, very calm, because I don't know, I think I have a great confidence in Susana. And I think I find in Susana as the two main things that I would ask to a PhD student. She's a hard worker, that's for sure. I mean, she never get tired or complains, and she's very careful. So you should have seen that if you ask her to send you one of her presentation, you will get like this 200 gig of slides, like 90 slides for 15 minutes, because she has everything well planned and clear in her mind. And she's also very perseverant, something that, you know, when you have to do something for her, like reading a form or checking a paper, she will knock to your door every time, and that's very good. And also she takes the punch very well, because not everything is rose, and some of our paper got somehow good and bad referees, as she said. And so these are the two things I ask for a PhD student. But the third thing Susana has, that you have experienced today, you might think that she was out of being nervous, is that she smiles and she's happy all the time. And this is really true. I mean, she's really brings something to the group, to the supervisor, and she's positive, always happy to learn new things and to help. She helped with the seminars in the PhD organized by PhD students. She was always the first to help to administer the cluster, the scientific cluster. She was happy to help with master students. So I mean, despite this has been a very sad year because we haven't seen each other for a very long time, and the next year will be even more sad because I know that I won't see you and you will not be around. And you know, all the nice things we have learned. So you might have seen this little color thing she had on the blackboard when she was talking. So this is Dia de los Muertos. So she comes every 2nd of November and makes this nice little skeleton colored, and she hangs them everywhere. And she brought us a lot of the Mexican culture in the lab. So yeah, so she was really a pleasure. I mean, of course, you've seen she has done a great scientific work, but she also did a nice social work in teaching us a lot of things. So, and also for me as a supervisor, I think the best rewards is that the first year I talked to her, she was saying, you know, I don't know if I want to be in science. And I say, okay, this is normal. And then the second year, she said, no, maybe I want to be in science, but I want to move to something more biological. And I say, okay, that's already a step ahead. And then the third year, she said, you know what? I really want to work in this domain of soft matter and colloids and so on. And so this is quite remarkable for us. And for me, it was quite a satisfaction. And so this is why she's moving to one of the big cathedral of colloids and soft matter, which is Utrecht and the group of Marjolein, of course. And of course, she will miss French bread. We know that. But apparently, to what Frank says, she will love Dutch milk, right? Apparently, this is going to, and I'm sure that she will find a way to have her tacos somewhere, and this is something always you get. So I can always, I mean, I know that you are going to do great scientific work. You are going to work with great supervisors in a great group, so this is not a problem. I just wish that you say that you enjoyed so much the time in Paris. I hope you're going to enjoy it so much, and I only can thank you really for this time. And I hope, you know, I think that among these good things that can happen to you, I can only ask the last things that could be good for you, maybe in the new apartment that you will go to live in this Monday, if I understand well. Maybe the neighbors has a cat that will come to visit you often, and this will be just the cherry on top of the cake. So good luck for next week.
Thank you.
Okay. Look.
Emmanuel is mute. Yeah.
Okay, somehow couldn't access this part of the screen. Yes, so now I said that the jury is going to reconvene under a different link for the discussion and shaping up the report.
Yeah, just give me 1 second that I have to make Susana host so that...
I'm co-host, so I'm not so sure if it...
No, I will make you host.
Okay.
Full promotion.
Now you are full host. Now that you are, no, you are not a doctor yet, so but this is just...
But host, yes.
But now I can actually leave, and this place will remain open.
Yeah.
So then we come back to here to make the formal announcement, okay? See you soon.
Thank you. I think you have to move also to the other rig.